Hello and welcome to Sleepy Science. What if the most dangerous thing about time travel wasn't reaching the past, but discovering that the past might already contain you? You could meet your younger self, prevent your own birth, receive a message before it was ever sent, become the cause of the journey you haven't taken yet, or step into a future where centuries have passed while only hours passed for you. A wormhole might connect two different moments. A rotating black hole might twist the paths of time itself, and some theories suggest that the universe may prevent paradoxes before they can ever happen. These are not just science fiction ideas. Many of them come from real questions raised by relativity, quantum physics, causality, and the strange geometry of space-time. Even though no one has ever proven that traveling into the past is physically possible, in this video, you'll explore 60 of the deepest and most unsettling questions about time travel. From paradoxes and branching timelines to black holes, wormholes, entropy, and the possibility that the future may already exist. Before we begin, like the video and subscribe. Then settle in, because the deeper you follow time, the less certain the difference between past, present, and future begins to feel. What would actually happen if you traveled back in time? The first thing that would surprise you about traveling into the past is that, from inside your own body, almost nothing would appear to be moving backward. Your heart would continue beating forward, your thoughts would arrive one after another, your memories would keep accumulating, and a broken cup beside you would not suddenly leap from the floor and rebuild itself. In relativity, the time measured by the clock traveling with you is your own proper time. And even in theoretical spacetimes that contain routes into the past, you would still experience that personal time in its normal direction. The strange part would be the relationship between your path and the larger spacetime around you. General relativity allows certain mathematical geometries containing what physicists call closed timelike curves. Paths through spacetime that can return an observer to an event lying in the causal past of a later part of that observer's journey. Researchers have also shown that if a traversable wormhole could exist and its two entrances could acquire the right time difference, the geometry could in principle behave like a time machine. But this is an enormous if. No traversable wormhole has ever been observed. No human has ever traveled backward in time. And the kinds of space-time structures required may demand forms of matter or energy that cannot exist in the necessary quantities. Quantum effects may create further obstacles before such a machine could ever operate. So imagine, purely within the theory, that somehow those obstacles were solved and you entered a machine tonight. You would not watch clocks spin backward as you traveled. You might instead follow an entirely forward-moving personal journey and emerge into a region of space-time that other clocks label as belonging to an earlier date. To you, the trip could feel like entering somewhere and later stepping out. To the people outside, however, something far stranger would have happened. A person carrying memories of tomorrow would now be standing in yesterday. That distinction matters because popular stories often treat backward time travel as though the universe itself were being rewound. But relativity suggests a very different picture. You are not forcing every atom in existence to reverse its history. You are changing the route your own world line takes through spacetime. The road curves in such an unusual way that later for you could correspond to earlier in the surrounding history. And that immediately creates a deeper problem. The moment you arrive, you become part of that earlier world. Air molecules collide with your skin. Light reflects from you. The floor supports your weight. Anyone who sees you receives information that, from their point of view, came from the future. You are no longer simply observing history from outside it. You are physically embedded in it. Yet physics currently cannot tell us what nature would ultimately do with such a situation, because we have never discovered a real region of space-time where macroscopic backward time travel can be tested. General relativity tells us that certain strange causal geometries can be written down, while quantum theory hints that nature may resist their formation. That leaves you with one of the most important truths about time travel. Science has not shown that you can go into the past, but neither is the idea merely a fantasy invented by movies. It grows from genuine features of our best theory of gravity, pushed into extreme territory where the equations allow possibilities the real universe may never permit. And perhaps the most unsettling part is how ordinary the journey might feel from your seat. No reversed heartbeat, no backward thoughts, no sensation of time flowing the wrong way. You would simply continue moving into your next moment, only to discover that the rest of the world calls that moment its past. Could you change the past without destroying your own future? Changing the past would not necessarily make the universe explode. The real danger is quieter and far more difficult to escape. You could remove the cause of the very action you have already performed. Imagine that decades from now a particular event convinces you to build a time machine. You return to an earlier year and successfully prevent that event from occurring. Nothing obviously needs to shatter. The stars do not disappear. Space-time does not have to tear open. And there is no known law saying a paradox should release some catastrophic burst of energy. Instead, a logical wound appears in the history itself. If the event never happened, why did the older version of you decide to travel back and prevent it? And if you never made the journey, what prevented the event? The contradiction is not between two objects colliding. It is between the causes required for the same history to exist. This is why physicists studying hypothetical closed timelike curves do not usually treat paradoxes as magical disasters. They ask whether the laws of physics could permit only histories that remain globally consistent. In studies of particles interacting with their own earlier paths around a time machine, researchers have found self-consistent trajectories in which the traveler can influence the past but cannot arrange events into a logically contradictory history. In some models, what initially looks like an impossible paradox develops into a more complicated sequence of interactions that still closes consistently. That possibility changes what changing the past might mean. Perhaps you could move a chair, speak to someone, leave an object somewhere, or interfere with events in countless small ways. Yet every successful action would already fit inside the history that eventually produced you. You would have freedom to act locally, but not freedom to create an impossible global story. This would be a strange kind of limitation, because nothing would necessarily feel like it was controlling you. You might decide freely to take one action and discover that circumstances redirect its consequences. You try to prevent something, but your intervention becomes one of the reasons it happens in the form history already contained. Or your action succeeds, but only because the version of the past you remembered always included the consequences of your visit. Theoretical physics has not established that nature actually enforces such a rule, and other approaches to quantum mechanics and spacetime suggest different ways causal contradictions might be avoided. What matters here is that the familiar idea of destroying your future is not a well-defined physical process like burning a document. Your future is a network of causes, parents meeting, decisions being made, information being transmitted, technologies being created, and countless interactions converging on the moment from which you departed. Altering one piece does not automatically erase you like a picture fading from a photograph. The real question is whether a complete space-time can contain both your departure and your intervention without demanding that the same event both happen and not happen. General relativity can describe unusual geometries in which causal loops exist, but constructing a physically realistic time machine remains speculative, and quantum effects may prevent such structures from forming in the first place. So if backward time travel ever became possible, changing the past might turn out to be less like editing a saved file and more like discovering that history is a structure with conditions you cannot casually violate. You might touch the past, you might influence it, you might even become one of its hidden causes, but whether you could genuinely replace what happened with something incompatible with the future that sent you there is precisely where ordinary intuition fails. The deeper question is not whether the past would allow you to act, but whether reality would ever permit you to create a history that has no coherent reason for existing at all. What happens if you meet your younger self? Seeing your younger self across a room would create a situation far stranger than simply meeting someone who looks exactly like you, because the two of you would share one history only up to a certain point and then arrive at that moment carrying radically different amounts of information. If backward time travel was somehow possible, physics gives us no reason to expect the two versions of you to merge, cancel each other out, or react physically simply because they are the same person at different ages. You could, in principle, occupy the same room as two separate physical bodies, representing different points along the same life. The younger you would possess only the memories formed before that day, while you would carry everything that happened afterward. People they have not met, places they have never seen, fears they have not developed, and experiences that have not yet reshaped their brain. Even your bodies would no longer be perfect copies. Human tissues accumulate somatic mutations throughout life, while learning and experience continuously alter patterns of neural connection, meaning the older person standing there would be biologically and mentally different from the younger one, despite sharing the same origin. And this is where the meeting becomes more interesting than the usual science fiction image of two identical people staring at each other. You could remember exactly what it felt like to be them, but they could not remember becoming you. You might know the reason they are secretly worried that week, the place where they hid something years ago, or a sentence they have never told another person. Those details could convince them that you are not simply a stranger who resembles them, but proving who you are would immediately create another problem. The moment your younger self learns something about their future, their experience is no longer identical to the experience you remember having at that age. They now possess information you did not possess when you originally lived through that moment. And information can change a person long before it changes an event. Imagine telling your 18-year-old self that a friendship they consider permanent will soon disappear. Even if they make exactly the same outward decisions afterward, they may interpret every conversation differently. Tell them that they eventually succeed at something they are currently terrified of attempting, and the uncertainty that once shaped their behavior may weaken. Memory itself is not a perfectly frozen recording. Experiments on human memory show that recalling established memories can return aspects of them to a changeable state before they are stabilized again. So the older, you would not arrive as a flawless archive of an untouched past either. You would be meeting the person you remember being through a memory system that has continued evolving for years. Perhaps that is the most unsettling part of the encounter. You might expect recognition, but instead discover distance. The younger person might have values you abandoned, ambitions you forgot, or fears that now seem almost foreign. And as you listen to them, the question slowly shifts. You stop wondering what advice you should give, and begin wondering which of you deserves to be called the real you. The child was real. The adult is real. Yet neither contains the entire person. Meeting your younger self would not necessarily reveal that identity is duplicated. It might reveal that identity was never a finished object in the first place. You would be looking at the beginning of a process while standing inside one of its later results. And for a quiet moment, your own life would become visible not as a single unchanging self, but as something continuously becoming. Could you accidentally prevent your own birth? The most dangerous thing you could do before your own birth might be nothing more dramatic than making someone 30 seconds late. Your existence depends not merely on your parents eventually having a child, but on an extraordinarily specific reproductive event involving a particular egg and a particular sperm. Human sperm cells are not genetically interchangeable copies. During the formation of reproductive cells, chromosomes are shuffled and recombined, producing enormous variation from one gamete to another. Sequencing tens of thousands of individual human sperm has directly revealed extensive differences in their patterns of genetic recombination. That means if the circumstances of conception changed enough for a different sperm to fertilize the egg, the resulting embryo would carry a different genetic combination. Your parents could still have a healthy child at roughly the same time, raise that child in the same house, and even give them the name you eventually received, but biologically, that person would not be you. Now imagine what this means for a traveler moving through the months before their conception. You would not need to deliberately separate your parents. You might simply stop one of them to ask a question, cause them to miss a bus, convince them to attend a different dinner, or delay an evening by an hour. Most such changes would lead to nothing important, of course, and there is no scientific way to calculate exactly which tiny disturbance would alter a particular conception. But reproductive biology makes the underlying vulnerability real. The exact genetic individual produced depends on which gametes participate in fertilization, and those gametes contain different combinations created during meiosis. Move farther backward and the problem grows almost impossibly large. The same condition applies to your parents, and their parents, and the generations before them. A different meeting, illness, migration, missed train, surviving soldier, postponed wedding, or changed reproductive moments somewhere in your ancestry could eventually lead to a completely different set of descendants. This does not mean history is literally balanced on every footstep in the exaggerated way movies sometimes suggest. Many disturbances disappear without meaningful consequences, and backward time travel itself has never been demonstrated. More importantly, science cannot tell us what would happen to an already existing adult traveler if that traveler somehow prevented the conception that originally produced them. There is no established physical law saying you would become transparent, slowly disappear, or suddenly cease to exist. Those familiar images are storytelling devices, not measured physics. The part we can say something meaningful about comes from biology, recreating exactly the same human being after sufficiently disturbing. The chain of reproduction would be extraordinarily difficult because you are not an inevitable output waiting to appear whenever the same two family names meet. You are one particular genetic outcome among a vast number that could have occurred, and that leaves you with a quieter realization than the usual paradox. Long before you ever made your first choice, an immense chain of contingent events had already narrowed possibility toward you. If you could walk backward into that chain, you might discover that preventing your own birth requires no grand act against history at all. It might require only changing one ordinary evening enough that, when two cells finally meet, the person who begins is someone else. Would you remember a timeline that you erased? If you erased yesterday, what exactly would be left inside your head to remember it? Movies often give the time traveler a special privilege. History changes for everyone else. Photographs transform, people disappear, entire lives are rewritten. Yet the traveler somehow remembers the original world perfectly. It is a powerful storytelling idea, but physics has never established such a protection for memory. A memory is not something floating outside time. It is a physical state of your brain, maintained through patterns of neural connections and biological activity that were created by events in your own history. So if you truly replace the entire chain of events that produce those brain states, there is no known law guaranteeing that the memories would survive the replacement. The deeper problem is that modern physics does not actually contain a standard mechanism called erasing a timeline. In general relativity, space-time is normally described as a connected history of events, not as a cosmic document that repeatedly saves over its previous version. Some theoretical models containing closed timelike curves instead demand histories that remain internally consistent, while quantum proposals for dealing with such curves offer different mathematical ways of avoiding contradictions. There is no experimentally confirmed rule telling us that a traveler keeps memories from a history that ceases to exist. There is, however, another possibility that sounds similar while meaning something completely different. Suppose going into the past did not overwrite your original history at all, but placed you into an alternative history while your brain continued carrying information acquired before the journey. Then you could remember people and events that nobody around you had experienced. To them, your memories might sound like fantasies or predictions. To you, they would feel as ordinary and personal as childhood. But notice what has changed. You would not really be remembering an erased timeline. You would be carrying information from another history that had not necessarily been destroyed. That distinction is crucial because it separates a popular cinematic effect from what speculative physical models actually attempt to describe. and memory itself would add another complication. Human recollection is not an untouched recording that remains perfectly preserved for decades. The brain reconstructs memories, and each new experience can alter how an old event is interpreted. So even if a traveler somehow retained memories from another history, years spent inside the new one could gradually blur the emotional certainty of the old. You might remember a city building that nobody constructed, a friendship with someone who now treats you as a stranger, or the death of a person standing alive in front of you. At first, you could insist that your memories prove another past existed. Eventually, however, you would face a disturbing question. How would you prove that those memories came from another timeline, rather than from your own fallible mind? No photograph might match them. No database might confirm them. No other person might share them. The history you remember could become something scientifically inaccessible, even to you. And perhaps that is the strangest consequence of the idea. Erasing a timeline would not simply mean losing a world. If its information disappeared everywhere except inside one traveler's brain, then an entire history could be reduced to memory without evidence. A universe of experiences surviving only as someone saying, quietly and impossibly, "I remember when things were different." Could two versions of you exist at the same time? For a few impossible minutes, the universe could contain two bodies with the same childhood, the same parents, and the same birth date, and physics would not necessarily require either one to be a copy. This sounds contradictory only because you normally think of yourself as occupying one place at each date, moving steadily from younger to older. Relativity gives physicists a more useful picture. Your life can be represented as a path through space-time, often called a world line, with different points along that path, corresponding to different moments of your personal history. In ordinary life, that path never bends back far enough for two different stages of your life to appear in the same period. But a hypothetical closed timelike curve is precisely the kind of space-time path that can return an object to an earlier event, and theoretical work explicitly allows a traveler moving along such a path to encounter an earlier version of itself. Suppose you are 40 years old when you travel back to a Tuesday on which your 20-year-old self is still alive. During that Tuesday, there could now be two physical human bodies in the same region. 20-year-old you continuing normally toward the future, and 40-year-old you arriving after having already lived the next 20 years. This would not mean the universe had spontaneously manufactured an identical person from nothing. The older body would have followed a longer route through space-time and returned to a date already occupied by an earlier stage of its own history. In that sense, the two versions would be less like twins and more like 2 pages of the same biography, somehow lying open on the table at once. Importantly, they would not actually be identical. The older version would contain decades of additional memories, cellular aging, injuries, learned skills, and physical changes. Even if they began from exactly the same origin, they would represent different states of one continuing organism. This is also why the situation should not be confused with making a perfect quantum duplicate. Nothing has necessarily copied the complete physical state of the younger person. The older traveler has simply accumulated another stretch of personal history before returning. The strangest consequence appears when you ask how long the duplication could last. In an idealized loop, there might be 2 versions of you only between the moment the older traveler arrives and the later moment when the younger version eventually enters the same time travel route. Seen from outside, a room might contain 2 of you for 10 years, even though each version experiences only one continuous life. Closed timelike curve models have even been studied in situations where an object interacts with its earlier self, showing how radically ordinary ideas of before and after can fail once such paths are admitted. None of this demonstrates that humans can actually create such a path. No closed timelike curve suitable for time travel has ever been observed, and whether quantum physics would prevent one from forming remains unresolved. But the thought experiment teaches something surprisingly concrete about time. Your uniqueness does not come from the universe enforcing a rule that only one version of your body may exist on a particular calendar date. Under ordinary conditions, there is only one, because your path through space-time never doubles back. If that geometry changed, one person at one time might stop being such a simple statement. Two versions could stand beneath the same clock, breathe the same air, and disagree about which one belongs there. While both could truthfully say that, from the inside, they have never experienced anything except one uninterrupted life. What happens to the original you after you change the past? Here is the part time travel movies almost never explain. If you successfully change the past, what physical process would actually reach forward through history and erase the body that made the change? You are standing there with a functioning brain, circulating blood, atoms arranged into cells, and memories produced during years you have already personally experienced. There is no known mechanism in physics that would suddenly inspect the new history, decide that you are no longer supposed to exist, and dissolve you from reality. The familiar image of a traveler becoming transparent is storytelling, not a prediction of relativity or quantum mechanics. The real problem is much deeper. If your intervention made the circumstances that produced your journey impossible, then a theory of time travel would somehow have to describe a complete history containing both your physical arrival and the removal of the events that led to it. Different hypothetical models handle this difficulty differently, and none has been experimentally confirmed. Some approaches demand consistency, meaning that whatever you do in the past must fit into a history that can contain your journey without contradiction. Other quantum proposals allow stranger solutions, in which systems interacting with closed paths through time settle into states satisfying special consistency conditions rather than producing the simple cinematic sequence of change history, then disappear. David Deutsch's influential quantum treatment of closed timelike curves was developed precisely because classical versions of such situations can impose paradoxical constraints, while the quantum formulation can avoid some of them. The important lesson is that the original you is not a file stored by the universe that must be updated whenever history changes. At every moment, you are a physical system responding to your immediate surroundings. If some distant event in the past were somehow altered, physics would need a lawful connection explaining how that alteration changes your present state. It cannot simply invoke narrative logic. This is why the question becomes so difficult once you remove movie conventions. Perhaps an inconsistent change would never be permitted. Perhaps the traveler would persist because the history from which they came remains meaningful in some larger quantum description. Perhaps a complete theory of quantum gravity would reveal that the entire premise is impossible. We do not yet know. What we can say is that no accepted theory predicts the dramatic fading traveler so familiar from fiction. And that leads to a strangely personal possibility. If you could change everything that once led to your future yet somehow remain physically present, you might become a kind of causal orphan, a person carrying scars, knowledge, and experiences whose ordinary historical causes can no longer be found in the world around you. Your body would still tell one story while history told another. The unsettling question would no longer be whether you survive the change. It would be whether a person can still belong to a past that the rest of reality no longer contains. Could traveling back in time create an entirely new universe? Perhaps the most seductive escape from every time travel paradox is also the one most often misunderstood. You go into the past, change something, and instead of rewriting your own world, reality splits and gives your altered history a universe of its own. Quantum mechanics does contain interpretations in which reality can be described in terms of multiple branches, most famously the Everett or many worlds interpretation. But this does not mean physicists have discovered that a time traveler literally creates a fresh universe every time they interfere with yesterday. In many worlds, branching is associated with ordinary quantum interactions and decoherence. It is not a special cosmic emergency button activated by time machines. The apparent branches represent different outcomes, becoming effectively unable to interfere with one another as information spreads into the surrounding environment. If this picture of quantum mechanics is correct, branching would already be occurring in countless physical interactions around you, whether anyone travels through time or not. Time travel becomes interesting because some theoretical attempts to combine quantum mechanics with closed paths through time can be interpreted in ways that resemble movement between distinct histories. Deutsch's famous 1991 analysis explicitly connected closed timelike curves with the Everett interpretation and showed that quantum behavior around such curves could avoid certain classical paradoxes, but that work was a theoretical model, not evidence that parallel universes or usable time machines exist. Other researchers have proposed different quantum treatments of closed timelike curves, including post-selected models, and these approaches do not even make identical predictions, which tells you how unsettled the subject remains. Still, imagine what a branching description would mean conceptually. You leave a world in which a certain event occurred, arrive at an earlier stage associated with another possible history, and make a different choice. The altered future could then unfold without needing to overwrite the future you remember. Your original history would not have to vanish simply because another branch developed differently. In that picture, killing a butterfly would not magically rewrite the childhood stored in your memories. It would contribute to a different chain of events in the history you now inhabit. But even the phrase "create a new universe" can be misleading. Many worlds does not necessarily describe entire universes popping into existence from absolute nothing at each decision. It describes a universal quantum state whose components can evolve into effectively separate branches. You would therefore not be a god manufacturing cosmoses with every action. At most, within this speculative interpretation, your journey might connect your experience with a branch whose future diverges from the one you knew. And this produces a quieter, almost lonely consequence that fiction rarely explores. If you traveled back hoping to repair your own world, branching might deny you that victory completely. You could prevent a disaster here, save a life here, change everything here. Yet the history you originally left might remain untouched elsewhere in the larger quantum description. You would have created no rescue for the people you remembered. You would have entered a reality in which different people were spared. So the branching solution may protect logic, but it changes the emotional meaning of time travel. You would no longer be editing history. You would be choosing which history you continue into, and wondering whether the world you wanted to save is still unfolding somewhere you can never reach again. Can you return to the exact timeline you originally left? You could return to the same house, on the same date, beneath the same sky, and still have no physical test capable of telling you whether you had truly returned to the exact history you left. The phrase "same timeline" sounds simple, because everyday life gives you only one sequence of events to compare. But fundamental physics does not label histories with hidden serial numbers. In ordinary relativity, if space-time contained a path that carried you backward and eventually forward again, your journey would simply be part of one larger space-time geometry. There would not necessarily be a second timeline waiting beside it for you to accidentally enter. Closed time-like curves, which appear in some mathematical solutions of general relativity, describe paths capable of returning an object to its own causal past, and models built around them can contain globally consistent histories, even when an object encounters consequences of its own journey. But quantum descriptions complicate the meaning of returning even further. The world around you is constantly interacting with itself. Photons scatter from walls, molecules collide with air, thermal radiation escapes into space, and quantum information becomes distributed across enormous numbers of environmental degrees of freedom. Through decoherence, alternatives that were once capable of quantum interference can become effectively separate for macroscopic observers. If you imagined history in terms of quantum branches, returning to an exact previous branch would therefore require far more than reproducing the same visible surroundings. You would somehow need to recover an astonishing web of microscopic correlations extending through the environment. A coffee cup could be in precisely the same position. Your friend could say precisely the same sentence. And every clock you inspect could display the expected time while countless photons and particles already differed from those in the history you remember. Deutsch's theoretical work on quantum systems near closed timelike curves shows that quantum descriptions of time travel can behave very differently from classical stories about simply leaving and re-entering a single line of history, but none of these models has been experimentally demonstrated as a method of human time travel. This reveals something important that science fiction often hides. An exact timeline would have to mean much more than the same major events occurring again. If you demand literal physical identity, you are asking for the state and correlations of an unimaginably large portion of the universe to match what existed before you departed. Even a difference carried away by one photon could make the microscopic history distinguishable in principle. And if you yourself returned carrying memories of the trip, perfect restoration would already seem impossible in the most obvious sense, because the universe would now contain information that was not present in your experience of that moment the first time around. Perhaps the better question then is not whether you could find the right timeline, like choosing the correct road at an intersection. It is whether nature even contains the kind of separable, numbered timelines that our language encourages us to imagine. General relativity gives us space-time paths. Quantum mechanics gives us evolving physical states and, depending on interpretation, potentially branching descriptions. Neither gives you a cosmic sign saying you are now back in your original reality. So if you ever returned from the past and found everything apparently restored, the same people, the same city, the same life, you might experience one of time travel's quietest uncertainties. Nothing would look wrong. Nothing would need to feel wrong. Yet somewhere beyond everything you could measure easily, the universe might carry tiny traces of a history that never returned to exactly where it began. Could a message from the future create the event it warns you about? Warning from tomorrow could become dangerous for one unsettling reason. You might cause the disaster precisely because you tried to obey the warning. Imagine receiving a message at midnight containing only a few words. Do not enter the laboratory at 9 tomorrow morning. There will be an explosion. You believe it completely, so instead of following your normal routine, you rush to the building early to warn everyone. Security closes part of the facility. Researchers begin shutting down equipment in an unusual order. Someone interrupts an automated procedure, and that disruption eventually produces the very accident you were trying to prevent. Hours later, after surviving it, you realize why your future self sent the message. You send the same warning backward, hoping your younger self will somehow do better, and the circle closes. This would be more than an ordinary self-fulfilling prophecy. In everyday psychology, a prediction can influence behavior and help make itself true, but cause and effect still proceed normally from earlier to later. In a genuine time travel version, the warning would travel from the later event into its own causal past, allowing the effect of the disaster to participate in creating the conditions that produce that disaster. General relativity contains mathematical spacetimes with closed time-like curves where such cyclic causal structures can exist in principle. Although there is no evidence that nature provides a usable mechanism for sending messages through them, what makes the warning scenario fascinating is that nothing supernatural has to happen once the message arrives. The paper does not possess magical power. The receiver simply reacts to information, and those reactions alter ordinary physical events. A warning about traffic could make someone choose an unfamiliar road where the predicted collision occurs. A message telling engineers that a machine will fail could make them perform an emergency adjustment that places the machine in the state that eventually causes the failure. A prediction of political panic could provoke precautions that generate the panic themselves. The time travel component only needs to close the chain by carrying knowledge from the consequence back toward its earlier causes. Physicists studying simplified time machine models have found something surprisingly relevant. Situations that initially appear paradoxical can possess self-consistent trajectories in which an object's attempt to interfere with its earlier history becomes part of the very sequence that produces the outcome. In wormhole-based billiard ball models, for example, globally consistent self-interactions can replace the contradictory trajectory you might initially expect. That does not prove that the universe forces prophecies to fulfill themselves, and it certainly does not mean mysterious warnings from the future are occurring around us. These are theoretical investigations of what would follow if space-time permitted the required causal loops, but they expose a deep weakness in the intuitive idea that knowledge is always helpful. Normally, learning about danger gives you an advantage because the danger has causes independent of your knowledge. A future warning could destroy that separation. Your knowledge of the event might become one of the event's causes. The harder you try to escape it, the more precisely your actions might guide you toward it. Not because time possesses intentions, but because a self-consistent causal loop could include your attempt at prevention as an ordinary physical step, and that would create an almost unbearable uncertainty for the person receiving the message. Should you trust the warning and act, knowing your reaction might create it? Should you ignore it, knowing that ignoring it might be exactly what causes it? The message would appear to offer knowledge of the future, yet that knowledge could remove the comfortable boundary between prediction and participation. You would no longer be someone simply discovering what tomorrow contains. By learning about tomorrow, you might quietly become part of the machinery that brings it into existence. Can information travel through time without ever being created? Imagine opening an old notebook and discovering the complete design for a machine that no one has invented yet, only to spend the next 30 years building that machine and eventually send the same notebook back to your younger self. Now ask the question that makes the whole story collapse into something deeply strange. Who actually designed the machine? You learned it from the notebook, while the notebook contains information copied from the machine you built because you learned it from the notebook. The knowledge has a history, but apparently no moment of creation. This is known as a bootstrap paradox, or more broadly, an information causal loop, and it is one of the genuine conceptual problems that appears when theoretical physics permits closed timelike curves. Researchers distinguish these bootstrap problems from contradictions such as preventing the cause of your own journey. The loop can be perfectly self-consistent, while still leaving the origin of the information unexplained. Suppose a composer receives a symphony from her future self, memorizes it, publishes it, grows old, and eventually sends the score backward to the day she first received it. Every note has a perfectly identifiable path through time, yet nowhere along that path does anyone actually compose the music. This does not automatically violate conservation of energy, because information is not appearing as a burst of unexplained matter. The puzzle concerns causal origin. The score exists because it existed. The equation is known because it was already known. The answer becomes its own source. General relativistic models containing closed time-like curves can admit globally self-consistent histories, so logic alone does not necessarily eliminate loops of this kind, although there is no evidence that nature provides a real mechanism for constructing them. The physical details make the idea even more interesting. Real information requires a physical carrier, ink on paper, electrical states in a computer, patterns in a brain. Those carriers are vulnerable to noise, damage, copying errors, and thermal processes. If you copied a handwritten message and sent the copy around the loop repeatedly, tiny errors could accumulate unless the history somehow contained a mechanism that restores exactly the information required for consistency. Quantum proposals involving closed time-like curves deal with consistency in different ways and do not agree on one experimentally established description, which is another reason not to treat bootstrap information as something physics has shown can really occur. Yet the thought experiment exposes a remarkable distinction between knowing where information has been and knowing where it came from. In ordinary life, every book ultimately points backward toward an author, every discovery towards some process of discovery, every memory toward an experience. A closed causal loop could break that intuition without ever containing an obvious contradiction. The information could pass from future to past, from past back toward the future, and around again, complete at every point, yet authored at none. And if such a thing were physically possible, the strangest question would not be how the knowledge traveled through time. It would be whether the word created still means anything, when an idea can exist inside a circle with no first page? Could an object exist forever in a time loop without ever being made? Oh, watch sitting on your desk seems to demand a maker. But a watch trapped on a closed path through time presents a far stranger possibility. Perhaps there is no earliest day on which anyone made it at all. Picture receiving an old pocket watch from a mysterious visitor when you are 20. You keep it for 50 years, carefully preserving it. And at 70, you discover a way to travel backward and hand that very watch to your 20-year-old self. Its history now forms a circle. You received it because your older self delivered it, and your older self possessed it because you had received it decades earlier. No point in the loop contains the watch being manufactured. This is the material version of a bootstrap paradox. But adding matter creates problems that pure information can hide. A physical object has its own local history. Metal corrodes, surfaces scratch, lubricants break down, radioactive isotopes decay, molecules react, and every second experienced by the object contributes to its physical evolution. A closed time-like curve does not mean that the object personally experiences time backward. Along its local path, ordinary processes still unfold in their usual sequence. Theoretical studies of objects moving through wormhole spacetimes illustrate that a body can follow a path into its own past and even interact with an earlier stage of itself while remaining subject to ordinary local equations of motion. This creates a problem for the supposedly eternal watch. If you receive it with one scratch and return it 50 years later covered in hundreds of scratches, then the watch arriving at age 20 cannot simultaneously be the younger-looking watch you originally received unless the complete loop contains some process that restores it. For an exact closed history, the physical state at matching points must fit consistently. That makes an indestructible object simply circulating unchanged forever much harder to justify than the simple story suggests. Real macroscopic objects have thermodynamic histories, and maintaining precisely the state demanded by a perfect loop could require extraordinary conditions. Yet the existence of a closed world line would not necessarily mean that matter suddenly materializes from nothing at some particular instant. From the space-time perspective, there might simply be matter distributed continuously along the loop, with no unique earliest point at which you can say, here is where it began. Studies of self-consistency in spacetimes with closed, time-like curves have even found that ordinary global conservation laws need not automatically fail merely because causal loops are present. That distinction is subtle but important. The paradox is not necessarily that the universe creates a kilogram of metal without paying an energy bill. It is that the object's history lacks the kind of beginning you expect every manufactured thing to possess. A factory normally precedes a watch, a tree precedes a wooden chair, and a star precedes the atoms in your body. The loop removes that simple ancestry. Every stage points to another stage, and if you follow the chain long enough, you arrive back where you started. No known experiment shows that macroscopic objects can live on such paths, and whether physically realistic closed time-like curves can exist remains unresolved. But if one ever could, an object might confront you with a disturbing kind of existence. Not something that appeared from nowhere, and not something that was created at a forgotten moment, but something whose entire biography is a circle. You could hold it in your hand, trace every year of its journey, and still never find the moment when the universe first acquired it. Can a time traveler become the cause of their own journey? The reason you step into a time machine might be waiting for you in the past, wearing your own face. Imagine spending your entire life obsessed with a mysterious event from childhood. One night, a stranger appeared outside your home, told you that traveling through time was possible, and disappeared before anyone could identify him. That encounter becomes the reason you study physics, the reason you devote decades to building a machine, and eventually the reason you travel back to investigate what happened. But when you arrive on that childhood night, circumstances force you to approach your younger self, and suddenly you recognize the scene. The mysterious stranger who inspired your life was you. Your journey now appears to cause the motivation that eventually causes the journey. This kind of structure is called a causal loop, and it can arise mathematically in spacetimes containing closed time-like curves, where an object or observer can return to an event in its own causal past. General relativity contains solutions with such curves, although no usable time machine or macroscopic closed time-like curve has ever been observed. What makes the situation so unusual is that every local event can still have an understandable cause. You study time travel because of the childhood encounter. You make the journey because your studies succeed. The childhood encounter occurs because you make the journey. Nothing within the circle necessarily happens without an immediate explanation, yet the complete chain has no ordinary starting point. Researchers studying hypothetical wormhole time machines have shown that classical systems can possess globally self-consistent trajectories in which later portions of a path interact with earlier portions of that same path. This does not establish that the universe actually permits a person to become the cause of their own voyage. These are theoretical models exploring what the laws would require if such space-time structures existed, but they expose something deeper about the way you normally understand causation. You instinctively search backward for beginnings. A decision came from an experience. The experience came from an earlier event, and eventually you expect to reach something that started the sequence. A causal loop refuses to provide that first link. Its events support one another around a circle, and if your entire decision to travel through time existed inside such a loop, asking, "Who started this?" might be like asking where a circle begins. Every point has something before it. Every action has a reason, and yet the journey as a whole may have no first cause sitting quietly at the beginning of history. The strangest part would be realizing that you spent your life chasing the person responsible for sending you through time, only to arrive in the past and discover that responsibility had been following you from the beginning. Could trying to prevent the future be what creates it? You might reach the past, believing you are there to stop a catastrophe, only to discover that history needed your attempt to stop it in order for the catastrophe to happen at all. Suppose you witness a major accident decades in the future and learn enough about its early circumstances to believe you can prevent it. You return to the critical day, move equipment, redirect people, close a road, or interfere with some apparently harmless detail. Every action makes sense from your perspective because you know what you are trying to avoid. Yet those interventions alter ordinary chains of cause and effect. Someone takes a different route. A machine is restarted under different conditions. A worker enters a place they would otherwise have avoided. And eventually the sequence you feared emerges from the very changes you introduced. Nothing mystical needs to push events toward destiny. The unsettling possibility comes from self-consistency. In theoretical spacetimes with closed time-like curves, physicists have investigated whether local events can fit together into a complete history without contradiction. The proposed self-consistency principle says, roughly, that only local events capable of belonging to a globally consistent history can occur. It is a theoretical way of handling causality in these unusual models, not an experimentally established law of nature. One of the clearest demonstrations comes from simplified wormhole models involving a billiard ball. A naive trajectory can appear paradoxical because the ball travels into the past and interferes with its earlier motion, seemingly preventing itself from entering the wormhole. But detailed calculations found self-consistent alternatives in which the collision changes the earlier ball's trajectory in just the right way for the later interaction to occur. Remarkably, the problem can yield many consistent solutions, rather than the simple contradiction intuition predicts. A human attempt to change history would be incomparably more complicated, so the billiard ball result cannot simply be promoted into a rule governing people. Still, it reveals an important idea. Preventing an event and causing it are not always cleanly separated once causal paths can return to their own past. Your intention does not determine the physical role your actions play. You may act to produce one outcome while the consequences of those actions produce another. In ordinary life, this already happens without time travel. Attempts to avoid risks can sometimes create new risks. A closed causal structure would add a much stranger layer because the future motivating your intervention could depend on that intervention having occurred. And then the word prevent begins to lose some of its certainty. You might know exactly what future you refuse to accept, travel across decades to fight it, and use every choice available to you, only to realize at the end that history was never defeating your effort from the outside. Your effort was one of the ingredients from which that history had always been made. What if every attempt to change the past was already part of history? You arrive in the past ready to rewrite history, only to find evidence that history has been waiting for you all along. Perhaps an old photograph already contains a blurred figure wearing your coat. A diary describes a stranger saying the words you're about to say, or an unexplained event from your childhood suddenly makes sense because you are the person who caused it. This is one of the most intriguing ways physics can imagine avoiding the contradictions of backward time travel. The past does not change when you visit it because your visit was always one of the events that made that past what it was. General relativity describes an entire space-time rather than a universal clock continually replacing one version of reality with another. So in a hypothetical space-time containing closed time-like curves, a traveler's departure, journey, arrival in the past, and later consequences could all belong to one complete geometric history. Researchers studying such space-times have proposed a self-consistency principle. A local event may occur only if it can fit into a globally consistent solution of the physical laws. Importantly, this is a proposed way of handling time travel geometries, not a confirmed rule of our universe. The idea produces a subtle change in how you should imagine your mission. Suppose you travel back to stop a famous ship from sinking. You are not necessarily facing an invisible force that pushes your hands away from the controls. You might successfully speak to the crew, move equipment, investigate the danger, and make dozens of genuine decisions. Yet if there is only one self-consistent history, whatever you actually do must be compatible with the historical world from which you eventually departed. Perhaps records you once considered incomplete already contained the consequences of your intervention. Perhaps a mysterious warning mentioned in an archive was yours. Perhaps survivors existed partly because you helped them, meaning the history you thought you were about to change had always included your presence. This makes time travel less like editing a document and more like discovering missing sentences in a document that was already complete. There is even a technical reason this possibility is unusual. Ordinary physics often works like an initial value problem. Specify the state of a system now and calculate what happens later. Closed time-like curves can turn the situation into something closer to a global constraint because events farther along the traveler's path can reconnect with earlier events, forcing the full history to fit together rather than allowing every locally imaginable sequence. Theoretical studies show that self-consistency can restrict possible histories while still allowing substantial local behavior, although different models can have multiple consistent solutions rather than one predetermined script. So this idea does not prove that destiny controls you, nor does it prove that backward time travel exists. It suggests something stranger. If the universe admitted a single consistent history containing time travelers, your choices in the past might be completely real while never producing a second version of what happened. You would enter history believing you were an outsider arriving to rewrite it, slowly follow the traces left by your own actions, and eventually understand that there was never a version of the past without you. You were not changing history at all. You were finally discovering the part of history that had always been yours. Could the universe physically prevent you from creating a paradox? Perhaps nature never needs to solve a time travel paradox because it destroys the road to the paradox before you can enter it. This possibility is known as chronology protection, an idea most famously associated with Stephen Hawking, and unlike a rule saying that your actions must mysteriously fail after you reach the past, it asks whether the laws of physics might prevent usable paths into the past from forming in the first place. General relativity contains mathematical solutions with closed time-like curves, but a mathematical space-time is not automatically something the real universe can build. To create certain proposed time machines, You would need extreme geometries, such as specially arranged wormholes or other configurations that bring space-time close to developing a region where causal paths circle back on themselves. The boundary at which such closed paths first become possible is called a Cauchy horizon, and this is where quantum physics may become destructive. Empty space is not completely inactive in quantum field theory. Fields possess fluctuations even in vacuum. Calculations performed near hypothetical chronology horizons found that quantum effects can become extremely large in some models as spacetime approaches the formation of closed timelike curves. Kim and Thorne investigated whether vacuum fluctuations could destabilize a developing wormhole time machine, while Hawking later argued that the resulting stress energy and its gravitational back reaction might grow strongly enough to stop the chronology-violating region from forming. In simple terms, imagine trying to bend a road until its far end reconnects with its own past. Long before the connection becomes complete, quantum fields traveling around the nearly closed route could repeatedly return extremely close to where they began. Their accumulated influence might distort the geometry you are attempting to create, like a structure becoming increasingly unstable as you push it toward the configuration needed for the final connection. If that back reaction becomes sufficiently strong, the would-be time machine could collapse, deform, or otherwise become physically inaccessible before the first paradoxical journey ever occurs. There are additional obstacles. Traversable wormhole proposals involve unusual requirements concerning negative energy and violations of familiar energy conditions, and some geometries once proposed as time machines fail when one insists that their sources remain physically reasonable. Yet chronology protection remains a conjecture, not a theorem proving that the universe universally bans time travel. Semi-classical calculations combine classical gravity with quantum fields, but precisely where a chronology horizon becomes extreme, a complete theory of quantum gravity may be required, and physics does not yet possess an experimentally verified one. Later reviews therefore emphasize that no definitive universal chronology protection mechanism has been established. That uncertainty makes the idea more fascinating, not less. Nature already protects certain boundaries through physics rather than intention. Massive objects cannot simply accelerate through the speed of light, and unstable configurations can destroy themselves when pushed too far. A time machine might face a similar limit. You could spend centuries designing the perfect device, solve every engineering problem you understand, bring its two ends closer and closer to becoming a doorway into yesterday, and then discover that the final step always triggers physics you cannot overcome. The universe would not need to stop you from killing your grandfather, changing a war, or contradicting your own history. It could enforce causality much earlier and much more quietly, by making sure that no machine capable of asking those questions ever opens its door. What happens if you try to kill your past self? Few time travel scenarios expose the problem of causality as brutally as standing in front of your younger self and trying to make sure they never grow old enough to become you. Unlike preventing your grandparents from meeting, this version removes almost every unnecessary step from the contradiction. You are alive in the past only because your younger self survives long enough to become the traveler who made the journey. Yet you are now attempting to end that life before the journey occurs. If you succeed, the person who performed the act should never have reached the moment of departure. If you never depart, however, no older version of you should be present to perform the act. Theoretical physics does not tell us that your body would suddenly vanish or that the universe would explode. Instead, the problem is whether a complete trajectory through space-time can exist at all when its different parts demand mutually incompatible events. Physicists have explored a surprisingly clean analog using billiard balls and wormholes. A ball can be aimed so that it enters a hypothetical wormhole, travels into its own past, and then collides with its younger version in a way that seems capable of preventing the younger ball from entering the wormhole. This is essentially the mechanical skeleton of trying to eliminate your past self. Yet detailed calculations found something unexpected. Many apparently paradoxical initial conditions do not produce a contradiction with no solution. They can produce self-consistent trajectories in which the older ball strikes the younger one differently from the naive expectation, and the collision still leaves the younger ball on a path that eventually creates the older one. In some configurations, there are even multiple consistent solutions for the same initial setup, rather than one inevitable outcome. That does not mean a human assassin would be physically guided into missing, nor does it prove that the universe protects your younger self. These are simplified mathematical models inside hypothetical spacetimes, and no traversable route into our own past has ever been observed. What they demonstrate is subtler. Once a path can encounter its own earlier portion, ordinary assumptions about predicting the future from a starting condition can fail. The paradox may not force nature into nonsense. Instead, the complete history may have to be one of the histories that can exist without contradiction. Quantum models of closed timelike curves have also been constructed that handle self-interaction in very different ways, reinforcing the fact that we do not yet possess a single experimentally established theory describing what a real traveler would experience. So if you stood before your younger self with every intention of ending your own history, the scientifically responsible answer is not that some magical law would certainly save them. It is that our present theories do not allow us to predict a real event of this kind, but the thought experiment reveals something deeper. By attacking your past self, you would not merely be attacking another human body. You would be trying to remove an earlier section of the very physical path that brought your hand into that moment, asking reality to contain an action whose own success would erase the conditions required for the action to exist. Could a gun mysteriously fail every time you try to break history? A gun jams once and you call it bad luck. It jams 1,000 times, only when you aim at history, and suddenly it begins to look as though the universe has preferences. This is one of the most memorable versions of self-consistent time travel. You return to the past, aim at an event that must remain unchanged, pull the trigger, and something always intervenes. The cartridge misfires. Your hand slips. Someone opens a door. The target bends down at exactly the right instant. It is tempting to imagine an invisible force of fate arranging these failures, but no established physical theory predicts that paradox prevention would work this way. The self-consistency ideas studied in closed timelike curve models impose conditions on an entire history. They do not introduce a special field that detects dangerous intentions and sabotages weapons. In fact, classical studies of time travel analogues suggest something much stranger than repeated mechanical failure. When a billiard ball is sent toward a hypothetical wormhole in a configuration that appears capable of disrupting its own earlier motion, researchers found that consistent solutions can exist through ordinary collisions and altered trajectories. Some initial conditions permit several different self-consistent outcomes rather than one predetermined rescue mechanism. Applied cautiously to the gun scenario, that means consistency would not necessarily require the weapon itself to fail. Perhaps it fires normally but misses. Perhaps you are interrupted before firing. Perhaps the injury occurs but is not fatal. Perhaps the event you believed had to be prevented was misunderstood. Or, depending on what the true physics of time travel turned out to be, the entire premise might simply be impossible. The important point is that the gun must jam is not a law of nature. It is a dramatic way of representing a much broader requirement. If only globally consistent histories are allowed, then the final sequence of events cannot contain an outright logical contradiction. There is also a deeper mathematical surprise. In ordinary deterministic mechanics, you expect one complete future to follow from sufficiently precise starting conditions, but closed time-like curves can destroy that simple expectation. The same initial state may correspond to multiple consistent evolutions, meaning that the universe would not necessarily need to select one miraculous sequence of accidents. The unusual causal structure itself can make prediction non-unique. Quantum approaches complicate matters further, because competing models of closed time-like curves resolve paradoxes using different consistency rules and are not experimentally confirmed descriptions of actual time machines. So the eerie image of a perfectly functional gun failing at the one moment history is threatened should remain what it is: an illustration, not established physics. If backward time travel were possible, nature might preserve consistency through circumstances no traveler could recognize in advance. Or it might forbid the entire situation before the trigger was ever pulled. And perhaps that is more unsettling than a supernatural jam, because you could never know which ordinary detail around you was merely chance, and which one was the only path reality could consistently allow. Does time travel destroy free will? The most disturbing possibility is not that a time machine could imprison your body, but that it could make you wonder whether your choices were ever yours in the first place. Imagine knowing that tomorrow you will travel into the past and witness yourself making a particular decision today. When today finally arrives, can you choose differently simply because you now know what you supposedly did? It is tempting to conclude that time travel would instantly destroy free will, but physics does not actually say that. Free will is not a quantity that appears in the equations of relativity, and the existence of a closed timelike curve would not automatically turn you into a puppet following a predetermined script. What it would change is the relationship between your local choices and the complete history containing them. Some theoretical models of time travel require consistency, meaning that whatever actions occur must fit together without producing an impossible history. But researchers have also constructed deterministic models containing non-trivial time travel, in which observers can still perform arbitrary local operations without creating logical inconsistencies. In other words, consistency does not necessarily mean that a mysterious force chooses your actions for you. You could still deliberate, hesitate, change your mind, act impulsively, or make a choice for reasons that feel completely your own. The constraint would appear only when the entire web of events is considered together. This distinction matters because freedom and unpredictability are not the same thing. A decision can have causes and still be your decision, while a completely random event is not automatically an expression of freedom. Even more surprisingly, closed time-like curves do not always make physics more deterministic. Theoretical work has shown that some classical systems containing them can evolve in more than one consistent way from what appears to be the same starting condition. So allowing paths into the past can actually weaken ordinary predictability rather than strengthen it. Quantum models complicate the picture further because different proposed treatments of closed time-like curves impose consistency in different ways and can make different predictions. None has been verified as a description of real human time travel. So the question becomes philosophical as much as physical. Suppose you travel back and choose to order coffee instead of tea. Later you discover that historical records had always shown you ordering coffee. Did the record force your decision? Or did the record say coffee precisely because that is what you freely chose when the moment came? From inside your experience, there may be no sensation of compulsion at all. You consider both options, remember the consequences, and choose one. The complete space-time may contain that choice, but knowing that an event belongs to a complete history is not the same as identifying what caused the person to make it. This is why time travel does not give physics an easy proof against free will. It exposes a tension between two different viewpoints. From inside your life, decisions unfold through thought, uncertainty, emotion, and intention. From a hypothetical outside view of the entire history, those same decisions may simply appear as events occupying particular places in space-time. Perhaps time travel would not steal your ability to choose. Perhaps it would reveal something more unsettling, that a choice can be completely yours even if the universe already contains the moment in which you make it, leaving you to ask whether freedom ever required the future to be unwritten in the first place. If the future already exists, are your choices already waiting for you? Somewhere in space-time, could the final conversation of your life be just as real as the sentence you are hearing now? This question comes from one of the most profound interpretations of relativity, the block universe. In everyday experience, reality seems divided into three categories. The past happened and is gone, the present is real now, and the future has not happened yet. Relativity makes that division much harder to turn into a universal feature of nature, because observers moving differently through space-time do not always agree about which distant events are simultaneous. There is no single cosmic clock that divides the entire universe into one objectively shared now. This helped motivate the picture of space-time as a four-dimensional structure containing events at different times, much as space contains places at different locations. In the strongest block universe interpretation, your childhood, this moment, and your distant future all belong to that structure rather than reality, continually creating one moment and destroying the previous one. But there is an essential scientific caution. Relativity does not prove that the future already exists in the metaphysical sense people often assume. Physicists and philosophers have developed alternative pictures, including evolving block approaches. And Raphael Sorkin has explicitly argued that relativistic physics does not by itself force the conclusion that genuine becoming or an open future is impossible. So when someone says that Einstein showed your entire future already exists, they are moving beyond established experimental physics into an interpretation of what space-time means. Still, suppose for a moment that the block picture is correct. Would your decisions then be waiting ahead of you like objects placed in rooms you have not entered? Not quite. That language quietly imagines another time outside ordinary time from which someone could say the future already exists. But a four-dimensional block does not need an external present sweeping across it. Your future decision would simply occupy a later region of your world line, while your current uncertainty would occupy this one. When you reach the decision, you would still perform the physical process of deciding. Your brain receives information, weighs competing goals, retrieves memories, predicts consequences, and eventually produces an action. The existence of that event within the complete structure would not mean there is a second version of you ahead, somewhere consciously waiting for you to arrive. Nor would it mean that you should somehow be able to remember tomorrow. Information accessible to you still depends on causal connections, and your present brain contains records of earlier events rather than ordinary records of future ones. The block universe therefore creates a peculiar difference between existence and accessibility. A future event could belong to the geometry of space-time while remaining completely unavailable to the person you are now. And this is where the idea becomes quietly unsettling. You may spend tonight wondering which path you will choose tomorrow, experiencing uncertainty as something genuine and immediate, while a block description would portray the eventual choice as another part of the same space-time that contains your wondering. The uncertainty is still real as an experience because you do not possess the future information. Your deliberation is not meaningless. It is one of the processes through which that future event occurs. Whether nature truly should be understood this way remains unsettled, and alternatives such as evolving or crystallizing block models have been proposed precisely because the relationship between space-time, quantum uncertainty, and becoming remains conceptually difficult. But if the strongest block universe picture were right, the future would not be a destination sitting impatiently ahead of you. It would be another region of the structure you call your life, one you cannot yet see, cannot yet remember, and can reach only by continuing to become the person whose choices are written there. Could the past be fixed, even if you are allowed to visit it? A locked past would not necessarily keep you out of yesterday. It might simply refuse to become a different yesterday after you arrive. That distinction changes almost everything about backward time travel. You usually imagine the past as a recording that a traveler could reopen and edit. But relativity does not describe history as a sequence of saved versions being constantly replaced. It describes events as parts of space-time, and in hypothetical geometries containing roots into the past, your arrival could simply become another event located there. You could walk through an old city, speak to people, move objects, leave footprints, and make genuine decisions without producing a second version of what happened. Because those footprints, conversations, and decisions would belong to the past you had always come from. In this picture, there is no untouched original history hidden underneath your visit. If you remember that a window was mysteriously broken in 1985, and you later travel to 1985 and accidentally break it, you have not changed the record. You have discovered why the record always contained a broken window. This is closely related to the self-consistency principle explored in theoretical work on closed timelike curves, where locally allowed events must be extendable into a globally consistent history. But a fixed past would not mean you become a ghost unable to affect anything. Quite the opposite. Your effects could be real, measurable, and important. The limitation would be that you cannot transform an event you already know occurred into an incompatible event that did not occur. That is a much subtler restriction than simply saying the universe stops you. Think about visiting an archaeological site before it became a ruin. You might believe your presence gives you the power to rescue an artifact that history says was lost. Perhaps you hide it somewhere safe, only to learn that the object historians eventually discovered centuries later was the very object you hid. Your action succeeded. What failed was your assumption that success had to produce a new past. Theoretical studies of objects moving through wormhole spacetimes show that histories involving self-interaction can remain globally consistent even when the traveler strongly influences earlier events. None of this proves that the real universe permits such journeys. No traversable time machine has been observed, and whether the required space-time geometries can physically exist remains unknown. Yet the idea teaches an important lesson about what fixed could mean. The past might be immutable, not because you are forbidden from touching it, but because touching it was already included in what made it the past. You could enter history expecting to become its editor and instead discover yourself buried inside its evidence. Every action would still belong to you, every consequence would still matter, but there would be no earlier draft waiting to be replaced. The door to yesterday could open completely, while the story on the other side remains exactly the story that eventually led you to open it. What if there is only one self-consistent timeline? Suppose reality gives you countless choices inside a time machine, but accepts only one complete history in which all of those choices fit together. This is stronger than merely saying that paradoxes cannot occur, because it would mean that among all the imaginable ways events could unfold, only one entire timeline is physically realized. At first that sounds like simple determinism, yet closed time-like curves make the problem much stranger. In ordinary physics, you often specify what a system is doing now and use the laws of motion to determine what happens next. This is called an initial value problem in technical language, but the intuition is simple. Give nature a starting point and let the future unfold. A path that returns to its own past interferes with that logic, because part of the future can become one of the conditions affecting the earlier system. Now, the universe may need a complete solution that fits around the loop, rather than merely evolving forward from a beginning. Friedman, Morris, Novikov, Thorne and their collaborators explored precisely this issue and proposed that locally valid events in a spacetime with closed time-like curves must belong to a globally self-consistent solution. But here is the surprising part that is often lost in popular explanations. Self-consistency does not automatically guarantee that there is only one possible consistent history. In the famous wormhole billiard ball calculations, some starting trajectories produced one consistent solution, while others produced many. A later detailed analysis found entire classes of apparently paradoxical trajectories with infinitely many self-consistent outcomes. So, one self-consistent timeline would require nature to possess an additional rule selecting a single member from all the histories that might satisfy consistency. Physics has not established such a rule. Imagine arriving in the past at a railway station. There may be several actions that do not contradict your existence. You could sit silently, speak to a stranger, buy a newspaper, or leave immediately. If all four possibilities can be extended into complete, contradiction-free histories, self-consistency alone does not tell you why reality must select only one of them. A truly unique timeline would need the full physical state of the universe, together with whatever laws govern the time travel region, to determine one consistent solution and reject all others. That would make the timeline less like a story protected by fate, and more like an enormous boundary value problem in which every event has to fit with events on both sides of the temporal loop. Some later work using action principles has found that globally self-consistent trajectories arise naturally in specific classical models, but those models can still admit multiple consistent paths depending on the conditions. Quantum theories complicate the picture even more, rather than giving us one experimentally proven answer. So if only one self-consistent timeline truly existed, it would be a profound additional feature of reality, not something we can casually derive from the phrase time travel. You might feel uncertainty before every decision because you cannot see the whole structure, even though only one complete arrangement of those decisions ultimately works. From your perspective, the road would seem open. From the perspective of the entire space-time, perhaps only one road would ever connect back to itself without breaking, and that leaves you with a quiet question. When you stand at a fork believing several futures are possible, are you choosing which path becomes real? Or are you simply too small a part of the universe to see that only one path can complete the circle? Could time travel work only by creating branching timelines? A time machine may not need to change your past at all, and it may not need to manufacture a new universe either. The popular branching timeline idea offers an elegant escape from paradox. You travel backward, interfere with history, and your actions lead into a different branch, while the history you originally came from remains untouched. But physics does not currently tell us that backward time travel, if it were possible, must work this way. General relativity already contains mathematical spacetimes with closed timelike curves without requiring parallel universes. In those models, the traveler can move along an unusual path inside a single spacetime. Quantum mechanics then introduces several competing ways of describing what could happen when a quantum system encounters such a path. David Deutsch's influential model used a consistency condition for the quantum state, interacting with a closed timelike curve, and connected the discussion with the Everett interpretation, showing that certain familiar paradoxes can disappear in the quantum treatment. But Deutsch's proposal is not the only possible quantum model. A later approach, based on post-selection, produces different predictions and explicitly describes itself as inequivalent to Deutsch's theory. That disagreement matters because it means there is no experimentally established rule saying, enter the past and reality branches. In fact, the word branch can itself be misleading. In Everett-style quantum mechanics, a branch is not necessarily a completely new cosmos being constructed at one dramatic instant. Branch-like classical histories emerge as quantum systems become entangled with their environments, and decoherence makes different outcomes effectively unable to interfere in ordinary circumstances. The traveler would therefore not press a cosmic button that creates Universe B. If an Everettian description were correct, the journey would have to be understood as part of a quantum state that already admits multiple effectively separated histories. Even then, whether a traveler could move from one such history into another is a separate question. Ordinary many-worlds quantum mechanics by itself does not give you a machine for hopping between branches. And there are alternatives that attempt to preserve consistency without invoking branching in this sense at all. This is why saying that parallel timelines solve time travel moves too quickly. Branching can provide a conceptual picture in which changing an earlier event does not erase the history from which you departed, but it is neither experimentally confirmed nor known to be necessary. We do not yet possess a successful theory of quantum gravity telling us what truly happens when the geometry of space-time and quantum information are pushed into this regime. The deeper lesson is that nature may have several logically imaginable ways to deal with a traveler entering the past. Forbid the journey, constrain events to remain consistent, alter the rules of quantum evolution near the time loop, or perhaps allow something resembling separate histories. Physics has not chosen a winner. And so, the real mystery is not simply whether a road into yesterday would split in two. It is whether the universe even recognizes the sharp distinction between one timeline and many timelines that seems so obvious from inside your human experience of moving through time one moment at a time. How many universes could one time traveler accidentally create? If every tiny consequence of your visit to the past produced another universe, you could create more worlds before taking your second breath than you could ever hope to count. But that is also why the question may be asking for a number that physics does not actually define. In the popular version of many worlds, you make a decision and reality splits cleanly into two universes, one where you turn left and another where you turn right. Real Everettian quantum mechanics is subtler. Branches are usually understood as emergent patterns produced through decoherence, not as perfectly separated boxes stamped with identification numbers. A macroscopic object constantly interacts with its surroundings. Air molecules collide with your clothing. Photons scatter from your face. Heat leaves your body. Dust moves around your shoes. And each interaction can carry information about your physical state into the environment. Decoherence rapidly suppresses observable interference between macroscopically different alternatives, making them behave like effectively independent histories. Now place a time traveler in the past. The moment you arrive, you do not merely create one decision such as speak or remain silent. You introduce a vast new physical object, you, into an environment containing unimaginable numbers of interacting particles. Light bouncing from your body reaches walls and eyes. Air currents change. Microorganisms travel with you. Your gravitational influence, though tiny, is not zero. Every conversation generates sound waves and neural changes in the listeners. If an Everettian description applies universally, all of these processes participate in the continuing development of decoherent structure. Yet, asking exactly how many branches resulted from your arrival is not like asking how many roads leave a highway. There is no universally agreed, sharply defined way to count Everettian branches. Even the concept of a world is an emergent description rather than a fundamental numbered object in the underlying mathematical state. And modern work on branch counting exists precisely because naively counting decoherence-defined branches is problematic. Depending on how finely you distinguish physical differences, what looks like one macroscopic history could be described as containing enormously many finer alternatives. Change the level of description and the apparent count changes. That means statements such as one traveler creates 10 trillion universes have no scientific foundation. Even calling the number infinite can oversimplify the issue, because the deeper problem is not merely that the number is huge. It is that the theory does not provide a unique collection of discrete worlds waiting to be counted like coins, and the traveler would not be uniquely responsible for whatever branching occurred. If Everettian quantum mechanics is right, ordinary matter was already undergoing decoherence everywhere long before the traveler appeared. Stars emitting photons, atoms colliding, radioactive nuclei interacting with detectors, and biological systems exchanging information with their environments would all contribute to the same immense branching structure. You would add new correlations and new divergences, but you would not switch branching on. So perhaps one traveler could influence an astonishing range of future histories without literally creating a measurable stack of new universes. The unsettling realization is that the question, how many worlds did I create, might have no clean answer at all. You could return from the past believing you had split reality once, while the quantum description, if many worlds is correct, contains no privileged instant of splitting and no final counter displaying how many realities now exist. The universe would not branch around your importance. You would simply become one more interaction inside a branching process so vast that the boundary between one world and the next may exist more clearly in human language than in nature itself. Could you meet a version of yourself from a timeline that never happened? The strangest person you could ever meet might be someone who remembers being you in a life you never lived. If reality truly allowed branching histories and some form of time travel could move between them, then a version of you from another branch would not be a ghost, an illusion, or a copy created at the moment of meeting. They would be a person whose history shared part of yours and then diverged. Perhaps both of you remember the same childhood bedroom, the same teachers, the same family holidays, and the same fears at 15. But somewhere later, a physical event unfolded differently. One job was accepted instead of rejected. One accident happened instead of being avoided. One relationship continued instead of ending. From that point onward, two different chains of experience developed from what had once been nearly the same past. Quantum mechanics is sometimes interpreted through the many worlds picture, in which different outcomes can become effectively separated through decoherence. But physics has never shown that humans can travel between those branches, and it would be misleading to claim that alternate versions of you are known to be waiting somewhere accessible. Still, if such crossing were possible, the encounter would reveal something fascinating about personal identity. The other you might have your face and much of your biography, yet years of different experience could make their personality surprisingly unfamiliar. Human brains are continuously changed by learning, stress, habit, illness, relationships, and environment. A person who survived an event you never experienced could carry fears you do not understand. A version of you who made a different career choice might possess skills you never learned and memories connected to people you have never met. Even their body could gradually diverge through different injuries, diets, diseases, and ordinary biological aging. So which one would be the authentic you? Physics offers no reason to declare one original and the other counterfeit merely because their histories diverged. Both could trace themselves continuously back to a shared earlier state. What makes the situation even more unsettling is that one of those branches might be described from your perspective as a history that never happened, while for the person standing in front of you, it would be the only history that ever did. They might remember your world as the impossible alternative. You could tell them about years of your life and watch them recognize the beginning but not the ending. They could mention a parent who lived 10 years longer, a city you never moved to, or a child you never had. Those memories would feel as real to them as yours do to you. And suddenly the phrase, "what really happened," would stop having a simple answer unless you specify which history you mean. None of this is established evidence for parallel selves. It is what follows conceptually if branching histories are real and somehow traversable. But the thought experiment teaches something even without a time machine. You often imagine your identity as a single inevitable path leading from birth to this exact moment. Yet much of who you became depended on circumstances that could have unfolded differently. Meeting another version of yourself would make those abandoned possibilities physical. You would not be looking at who you were supposed to become. You would be looking at proof that there may never have been only one answer to that question. What happens if two time travelers change the same event differently? One traveler arrives to save a life. Another arrives to make sure that same person dies. And suddenly, time travel stops being a puzzle about one person fighting history and becomes a conflict between competing causes. Imagine two travelers approaching the same afternoon from different futures. Traveler A remembers a world in which a scientist dies before completing an important discovery, so A returns to prevent the death. Traveler B comes from a different future in which that scientist survives and later causes an unforeseen catastrophe, so B returns determined to prevent the survival. Both travelers possess internally reasonable motives. Both carry information from futures shaped by different outcomes, and both attempt to alter the same event in opposite directions. What happens next depends completely on what kind of time travel nature allows, and this is where the simple movie idea of changing history becomes inadequate. In a single self-consistent history, there cannot ultimately be two incompatible final outcomes for the same event. The travelers may interfere with one another, but the complete sequence would have to settle into one physically consistent history. Perhaps A saves the scientist from the original danger, while B's intervention creates a different fatal accident. Perhaps B fails, But their attempt becomes the reason the scientist later changes course and avoids the catastrophe B feared. The important point is that the traveler's intentions do not determine the structure of reality. Only the full chain of physical interactions does. In a branching model, however, their actions might correspond to different resulting histories rather than one replacing the other. Yet, even that is not as simple as saying A creates one universe and B creates another, because quantum branching is not known to occur specifically around human decisions, nor do we have evidence that a traveler could deliberately choose which branch to enter or leave. A third possibility is that usable backward time travel is impossible precisely because situations like this expose deep problems in global causality, and the conflict grows more complicated when information enters the picture. Traveler A may have prepared for B because A remembers historical records describing B's intervention, while B may know about A for the same reason. Their strategies could therefore depend on actions the other traveler has not yet performed from their personal perspective. You could end up with two people planning against effects that are already causes in the larger space-time structure. There is also no guarantee that either traveler correctly understands the future they are trying to create. History is not controlled by one event alone. Saving a person does not guarantee the world A remembers, and killing them does not guarantee B's preferred future, because countless later interactions can amplify, cancel, or redirect the consequences. This is a lesson from ordinary complex systems as much as from speculative time travel. Knowing one difference between two futures does not mean you know every cause that produced those futures. Two travelers could therefore battle over a moment they both falsely believe is the decisive turning point. After enormous effort, one might win and discover that the expected future still never appears. And perhaps that is the deeper problem with competing time travelers. Once multiple people can carry knowledge backward from different possible outcomes, history stops looking like a single object anyone can control. Each traveler arrives believing they understand what must be changed, yet each carries only a narrow memory of one path through an enormous space of possibilities. The fight would not simply be over which future deserves to exist. It would be over whether anyone inside time could ever understand enough of its consequences to choose a future deliberately at all. Could an infinite number of versions of you gather in one moment? A room containing 10 versions of you would already feel impossible, but a room containing an endless procession of you raises a much deeper question. Could one traveler loop through time so many times that the same moment becomes crowded with copies of a single life? In a hypothetical space-time containing a closed timelike curve, your personal path could return to an earlier date while your own internal time continues forward. If you repeated that journey again and again, the same calendar moment could, in principle, be intersected by several different stages of your world line. You might enter a room at noon, remain there for an hour, travel backward to 11:59, enter again, and repeat the process. An outside observer at noon could then encounter several versions of you, each one slightly older than the previous version, because every loop required additional personal time. Nothing here requires parallel universes or spontaneous cloning. Geometrically, it would be one continuous life crossing the same slice of external time multiple times. But going from many to infinitely many creates serious problems that simple diagrams tend to hide. Every version of you carries mass and energy. If 100 iterations occupy the room contains roughly 100 human bodies worth of matter at that moment. Continue increasing the number, and the gravitational influence rises with it. Heat accumulates, air is displaced, bodies collide, and eventually the travelers themselves change the environment so drastically that the conditions allowing the original loop may no longer remain intact. An actual person also ages along each journey. Repeating a 5-minute loop 1,000 times costs thousands of minutes of your own biological life, even if the outside clock keeps returning to the same hour. Reaching an infinite number of appearances would require an infinite sequence of trips, which means either an unlimited amount of personal time or some idealized mathematical construction that ignores ordinary aging, energy supply, wear, and gravitational back reaction. There are exotic space-time models in relativity where paths can behave in extremely counterintuitive ways. But mathematical possibility does not guarantee that matter could survive, or that the geometry could remain stable when filled with arbitrarily many copies of the same traveler. Quantum effects and the gravitational field produced by accumulated matter would make the situation even harder to treat realistically. So an infinite gathering of yourself belongs much more safely to the realm of idealized thought experiments than to anything physics predicts could be engineered. Yet the idea reveals something fascinating about what a copy really means in time travel. If 20 versions of you stood together, none would need to be counterfeit. Each would remember being the previous one, then leaving the room, looping through time, and returning slightly older. The youngest would look at 19 futures of their own body. The oldest would remember having once stood in every other position. And as the room filled, you would realize that time travel has not multiplied your identity so much as folded one continuous existence over the same moment again and again, until the question is no longer how many versions of you are present, but how many times one life can pass through the same piece of time before physics itself refuses to hold the fold. Can you travel into the future without any science fiction technology? You are already traveling into the future at a rate that can be changed simply by moving. And unlike almost everything we have discussed so far, this part of time travel is experimentally real. Einstein's relativity predicts that two people can experience different amounts of elapsed time between the same broad events if they follow different paths through space-time. Move very quickly relative to someone else, and your clock runs more slowly compared with theirs. Spend time in a stronger gravitational field, and your clock also ticks differently from one farther from that gravity. These effects are called time dilation, and they have been measured repeatedly with atomic clocks, satellites, aircraft, and fast-moving particles. You do not need a wormhole, a portal, or a machine capable of reversing causality. In principle, ordinary motion is enough. Imagine leaving Earth in a spacecraft capable of traveling extremely close to the speed of light. From your perspective, your heartbeat remains normal, your watch behaves normally, and every second feels exactly like a second. But when you eventually return, substantially more time could have passed on Earth than you personally experienced. You may have aged only a few years while people who remained behind aged decades or, at sufficiently extreme speeds, far longer. This is not because your body somehow freezes. Every chemical reaction in you, every thought, every biological process proceeds normally according to your own clock. The difference appears only when your elapsed time is compared with that of people who followed a different path. Nature demonstrates the same principle on much smaller scales today. Atomic clocks flown on aircraft do not remain perfectly synchronized with clocks left on the ground. GPS satellites require relativistic corrections because their motion and their weaker gravitational environment affect their clocks differently from clocks on Earth's surface. Without those corrections, navigation errors would accumulate. Even astronauts in orbit experience tiny differences in elapsed time compared with people on the ground. The effect is usually incredibly small at everyday speeds, which is why you never return from a car journey noticeably younger than someone who stayed home. To make a dramatic leap into Earth's future, you would need velocities enormously beyond anything humans can currently achieve for crewed travel, or access to an extreme gravitational environment where clocks differ greatly. But the principle itself is not speculative. Future-directed time travel is already built into tested relativity. There is also an important limitation. This kind of journey does not give you a button for returning to the year you left. If you use time dilation to let Earth advance 1,000 years while only a few years pass for you, those 1,000 years have still physically occurred on Earth. You have not skipped them in the sense of deleting them. You have simply experienced less time along your own path. Everyone you knew may be gone. Languages may have changed. Nations may have vanished. And the planet waiting for you could feel more alien than another world. That is what makes real future time travel so different from the fantasy version. The difficult part is not proving that time can pass at different rates. We already know that it can. The difficult part is realizing what success would mean. You could reach a future that others needed centuries to live through, but the price of that journey might be leaving your own century behind forever. How fast would you need to travel to reach Earth's distant future? To leave Earth in the 21st century and return after humanity has aged for centuries, you would not merely need to travel fast. You would need to move so close to the speed of light that ordinary ideas about speed begin to lose their usefulness. Relativity tells us that the faster you move relative to Earth, the less time you personally experience compared with people who remain behind. But the effect grows dramatically only when your velocity approaches light speed. At 90% of the speed of light, the difference is already significant, yet it is nowhere near enough to make a short voyage carry you thousands of years forward. At 99%, the separation becomes much larger. Push toward 99.9% and beyond, and a few years for you can correspond to many more years on Earth. To make truly enormous leaps, allowing centuries or millennia to pass outside while you age only a small fraction as much, you would have to add more and more nines after the decimal point. This happens because the speed of light is not simply another milestone you can eventually cross by adding enough engine power. For any object with mass, reaching light speed itself would require unlimited energy according to relativity. So the realistic question is always how closely you can approach it, never whether you can accelerate through it. And each extra step becomes brutally expensive. Accelerating a spacecraft from an already extreme speed to one even closer to light speed requires a disproportionately larger amount of energy. A vessel moving at such velocities would also face challenges almost absent from ordinary space travel. Tiny grains of interstellar dust could strike with tremendous energy. Even sparse gas atoms ahead of the spacecraft would become dangerous high-energy radiation in the ship's frame. Shielding, propulsion, heat management, and the enormous energy needed to accelerate and later slow down would become at least as important as the relativity itself. There is also no universal number called the speed required to reach the future, because it depends on how far forward you want Earth to advance and how much personal time you are willing to experience. If your goal is to reach a century ahead while aging considerably less, one velocity may suffice. If you want to watch 10,000 Earth years pass during only a few years of your own life, you must travel fantastically closer to light speed. This is one of relativity's strangest lessons. Enormous journeys into the future do not require you to exceed nature's speed limit. They require you to approach that limit so closely that the relationship between your clock and Earth's becomes profoundly unequal. You could look through your window and feel every second arriving normally, while far behind you, decades accumulate much faster by comparison. The speedometer would tell you that you were racing through space, but the deeper thing you would really be changing is how much history the rest of the universe is allowed to experience before you return. Could a journey near light speed let you skip thousands of years? You could, in principle, leave a civilization you recognize, spend only years aboard a spacecraft, and return to an Earth thousands of years older, but the journey would feel nothing like pressing fast forward. The key is that you would never experience your own time suddenly accelerating or disappearing. Inside the ship, you would eat, sleep, think, age, and watch your clocks advance normally. What changes is the amount of time accumulated along your path compared with the path followed by Earth. If your spacecraft traveled sufficiently close to light speed for long enough, relativity allows the difference between those two elapsed times to become enormous. A traveler could experience a relatively modest journey while thousands of years pass for people who stayed behind. This is the extreme version of the famous twin scenario. One twin follows a high-speed path away from Earth and later returns, while the other remains behind, and the traveling twin has experienced less time when they reunite. The asymmetry is not created simply because one person looks like they are moving. The traveler must change motion to leave, turn around, and reunite with Earth, so the two people follow genuinely different paths through space-time. For a voyage skipping thousands of years, however, the elegant physics quickly collides with brutal engineering. You must accelerate the ship to an extraordinary velocity, protect it during the journey, reverse direction if you intend to return, and then remove almost all of that tremendous speed without destroying the passengers. Even if you imagined an engine capable of maintaining a comfortable acceleration for the crew, the energy requirements would become enormous as the ship approached light speed. The interstellar medium would also stop looking harmless. Hydrogen atoms that are normally almost motionless relative to a spacecraft could strike at energies dangerous to both electronics and living tissue, while microscopic dust particles could behave more like high-speed projectiles than ordinary grains. And there is another consequence no engine can solve. A 1,000-year leap would be one way in the human sense, even if the ship physically returned to Earth. You could not simply undo the elapsed centuries by reversing your velocity. The people you left behind would have lived their lives. Generations would have been born and died. Coastlines and cities might have changed. Languages could evolve beyond recognition. And every institution you considered permanent might exist only in archives. Relativity lets you reduce the amount of time you experience. It does not stop the outside world from experiencing its own history. That makes near-light speed travel one of the few scientifically respectable forms of radical time travel, and perhaps one of the loneliest. You would not leap over thousands of years because those years failed to occur. They would occur completely. You would simply arrange your journey so that almost all of them happened somewhere else, while only a small number happened to you. Could you travel to the future by orbiting a black hole? Said to cheat tide, black hole could let the universe age faster than you without requiring you to race across the galaxy at nearly the speed of light. But only if you could survive one of the most extreme places nature allows. According to general relativity, gravity changes the rate at which clocks run. The deeper you are inside a gravitational field, the less time passes for you compared with someone much farther away. Around a black hole, this effect can become enormous. So in principle, a spacecraft spending time in a carefully chosen orbit could return to distant space having aged less than observers who remained far from the hole. But the phrase orbit a black hole hides several important limits. You cannot simply choose any distance and circle safely. Around a non-rotating black hole, there is an innermost stable circular orbit. Move farther inward than that, and an ordinary stable orbit no longer exists. You would eventually spiral toward the event horizon, unless your spacecraft continuously used thrust, and the closer you tried to remain, the more demanding the situation would become. A rotating black hole changes the geometry more dramatically. Space itself is dragged around by the black hole's spin, allowing matter orbiting in the same direction to remain stable closer to the horizon than it could around a non-rotating one. This is one reason rapidly spinning black holes appear so often in serious discussions of extreme gravitational time dilation. Yet surviving the orbit is another question. A small stellar mass black hole can produce devastating tidal forces near its horizon, stretching objects because gravity differs sharply between one end and the other. A supermassive black hole is surprisingly gentler at its horizon because the change in gravity across the length of your body can be much smaller. Even though the overall gravitational environment is immense, that makes a very massive, rapidly rotating black hole a more plausible thought experiment for a traveler. Even then, you would need to avoid the hot accretion disk, intense radiation, magnetic fields, infalling matter, and any instability in the orbit itself. And there is no simple promise such as 1 hour near a black hole always equals a century on Earth. The ratio depends on the black hole's mass and rotation, your exact trajectory, your distance from it, and how quickly you are moving. The famous extreme ratios shown in fiction require highly special conditions rather than merely approaching any black hole. Still, the underlying effect is genuine. If you could place yourself on a sufficiently relativistic path around a black hole and later escape, Your clock could record less elapsed time than clocks far away. You would not see your own life slowing. Your thoughts would feel normal. Your meals would take normal hours, and your heartbeat would remain ordinary to you. Only when you returned would the difference become undeniable. The black hole would not have thrown you through a magical portal into tomorrow. It would have allowed you to experience a shorter route through time, while the distant universe followed a longer one, turning gravity itself into a one-way machine toward a future you never had to personally live through. How far into the future could extreme gravity take you? There is no simple date stamped onto gravity's limit. In the equations of relativity, the difference between your time and the distant universe can become astonishingly large. But the closer you push toward the extreme, the less physically realistic your journey becomes. Gravitational time dilation grows as you approach a black hole's event horizon. To an observer who remains far away, a clock held closer to that horizon can run dramatically slower. At first, this sounds like a loophole allowing you to wait beside a black hole for a few minutes and emerge millions of years later. But the phrase, held beside, is doing enormous work. Around a non-rotating black hole, remaining motionless just above the event horizon would require continuous acceleration. The closer you tried to hover, the greater that required acceleration would become, rising without bound in the idealized limit as you approach the horizon itself. No material spacecraft could provide infinite thrust, and no human body could survive arbitrary acceleration. Free fall avoids that problem, but free fall creates another one. You do not remain suspended near the horizon indefinitely. You cross it in a finite amount of your own time. This is why the common statement that time stops at the event horizon is misleading. A distant coordinate description makes signals from an infalling traveler appear increasingly delayed and redshifted, but the traveler does not experience their own clock freezing. They continue forward, cross the horizon, and, if the black hole is simple enough, eventually encounter conditions from which escape is impossible. So, extreme gravity does not automatically provide an infinite waiting room beside the future. To gain a very large but survivable time difference, you would need a trajectory that keeps you in a strong gravitational region while still allowing escape, possibly around a rapidly rotating black hole, where stable or nearly stable motion can occur closer to the horizon. Even then, realistic limits come from radiation, tidal forces, orbital stability, fuel, and the black hole's environment. In mathematical idealizations, you can make certain time dilation factors arbitrarily large by approaching special limiting conditions. But physical black holes are not perfect equations. They accrete matter, lose energy through radiation over immense timescales, interact with their surroundings, and are unlikely to give you infinitely precise control over position and motion. There is also a profound difference between traveling far into the future and witnessing that future directly while you remain near the black hole. Light from the outside universe can reach you in unusual, strongly distorted ways, but you would not simply watch the whole cosmos play at unlimited fast-forward without consequences. Signals can become blue-shifted or red-shifted depending on your motion and location, and the radiation environment may become dangerous. The safest scientific statement is therefore both less dramatic and more remarkable. General relativity places no small universal ceiling on how much less time one traveler can experience compared with another under sufficiently extreme conditions. But every attempt to make the difference enormous pushes you toward environments where survival and escape become harder. Gravity can, in principle, carry you far beyond the era in which you were born, not by stopping time for you, but by changing how much of it your path contains. And if you ever returned after the distant universe had aged for ages, while only years had touched you, you might realize that the deepest price of gravitational time travel was not energy or engineering. It was arriving in a future where almost everything that once gave your life context had already become ancient history. Could 1 hour for you become centuries for everyone else? 1 hour on your wrist could, in principle, correspond to centuries somewhere else, but only if you placed yourself in conditions so extreme that ordinary life has almost no equivalent for them. Relativity does not require every clock in the universe to accumulate time at the same rate. What matters is the path each clock follows through space-time, and two observers who separate and later compare clocks can discover that dramatically different amounts of time have passed for them. To turn a single hour of your experience into a century for distant observers, the difference would have to be enormous. Their clocks would need to advance roughly 1,000,000 times more than yours. Extend the goal to several centuries, and the ratio grows into the millions. Relativity allows such enormous differences mathematically, but achieving them physically is the difficult part. One route would involve motion extraordinarily close to the speed of light. Another would involve remaining in an intensely curved region of space-time, such as near certain idealized configurations around a black hole. In either case, your own hour would feel completely ordinary. 60 minutes would still contain 60 familiar minutes. Your thoughts would not stretch, your heartbeat would not seem frozen, and a candle beside you would burn according to the same local rhythm as your body. The enormous difference would become meaningful only when your clock was compared with clocks that followed very different paths. This is one of the most easily misunderstood parts of time dilation. There is no sensation called being slowed down. Every process traveling with you shares your local time. If you drank a cup of tea during that hour, the tea would cool normally from your perspective. If you listened to music, the song would not last a century. Meanwhile, far from your extreme trajectory, generations could theoretically be born, grow old, and disappear before your hour ended. Yet creating a ratio that large would push technology far beyond anything humanity possesses. Near light speed travel would demand extraordinary energy and protection from radiation and interstellar matter. Extreme gravitational environments introduce their own problems of stability, tidal forces, heat, and escape. You also cannot simply stand at a magical location where 1 hour always equals 100 years. The ratio depends on the entire physical situation and on which observers you later compare. Still, the underlying principle is real enough that smaller versions are routinely measured with precision clocks. What changes at the extreme is not the rule, only the scale. And this leads to a strange realization about the meaning of a short life. If you somehow engineered such a journey, you could personally experience only an afternoon, while the society that launched you passed into legend. From inside your cabin, almost nothing would announce that history was racing ahead elsewhere. Then you would return, look at a clock that had once agreed with yours, and discover that your single hour had become the missing centuries of everyone else. Why is traveling into the future much easier than traveling into the past? Nature already gives you roads into the future, but every proposed road into the past seems to demand that space-time do something far more dangerous. Bend causality back onto itself. This is the fundamental reason future-directed time travel is so much easier. Traveling into the future faster than someone else does not require time to reverse, history to be rewritten, or causes to occur after their effects. Relativity simply allows different observers to accumulate different amounts of time. You can move very quickly, experience strong gravity, and later reunite with someone whose clock has advanced farther than yours. Every event still points forward along your personal history. You remember departure before arrival. Your heartbeat continues in one direction. Light signals still travel through the local causal structure in the ordinary way. Nothing requires the universe to explain how an event can destroy the conditions that produced it. Backward time travel is different because reaching your own past would require a path through space-time that eventually returns to an event lying behind part of your own history. General relativity contains mathematical solutions with such closed paths, but producing them in a physically realistic universe is much harder than merely exploiting time dilation. Proposed mechanisms often involve extreme structures such as traversable wormholes, rapidly rotating geometries, or other arrangements whose physical requirements may be impossible to satisfy. Traversable wormhole models, for example, typically require unusual distributions of energy that do not resemble ordinary matter, and quantum restrictions place severe limits on how negative energy can behave. Even if a suitable geometry could somehow be created, backward travel immediately threatens the normal organization of cause and effect. A signal might return before it was sent. An event could influence the conditions that produce the event itself. Physics must then decide whether such loops are forbidden, forced to remain consistent, split into some quantum description, or handled by rules we have not yet discovered. Future travel needs none of this. It already occurs whenever two clocks follow sufficiently different trajectories, which is why relativistic clock corrections are part of real technology, while machines traveling into yesterday remain hypothetical. There is also an important asymmetry hidden in ordinary experience. The future is already inside your light cone. Signals and objects can move from your present into later events without violating the local speed limit. Your own past lies behind you in the causal structure. Reaching it would require more than moving quickly, because accelerating faster does not rotate your personal future into your past. Even approaching light speed indefinitely still carries you forward. This is why building a faster spacecraft could dramatically increase how far into Earth's future you reach. Yet no amount of ordinary acceleration gives you a route to last Tuesday. You would need space-time itself to possess a shortcut or loop with properties radically different from the paths available around us. Perhaps a deeper theory of quantum gravity will someday show that such loops are possible under rare conditions. Perhaps it will prove that nature protects causality too strongly for them ever to form. But today the divide is clear. Traveling far into the future asks you to exploit laws we have already tested, while traveling into the past asks the universe to reveal whether those same laws can be pushed until the order of cause and effect begins to fold. That is why one form of time travel belongs to experimental physics, while the other still waits at the boundary between mathematics and possibility. Could a wormhole connect today with the distant future? A doorway open today could, in theory, have its other side waiting centuries ahead, but only if a wormhole could exist in a form that physics has never yet observed. In general relativity, a wormhole is a hypothetical tunnel through space-time connecting two separated regions by a shorter internal route. The important detail is that the two entrances, often called mouths, do not have to remain synchronized with the outside universe forever. Imagine creating a traversable wormhole with one mouth beside Earth and the other initially nearby. At first, clocks placed beside both mouths could agree. Now suppose one mouth experiences a very different history from the other. Perhaps it spends years moving at enormous speed, or perhaps it remains near an intense gravitational field where time passes differently relative to Earth. Relativity tells us that the two mouths could accumulate different amounts of elapsed time. One might age only a few years while centuries pass beside the other. If the wormhole's internal connection somehow remains intact throughout this process, entering one mouth could then link you not merely to another location, but to another external date. This is the remarkable feature that turns an ordinary space-time shortcut into something resembling a bridge between eras. You would not necessarily feel yourself traveling for centuries inside the tunnel. In idealized models, the internal journey might remain short, while the clocks outside the two mouths disagree dramatically. One entrance could stand beneath a sky you recognize, while the other opens into a civilization that has had hundreds of additional years to change. But this possibility rests on several enormous assumptions. We have never discovered a traversable wormhole. The simplest wormhole-like solutions associated with black holes are not safe tunnels you could cross and return through. Keeping a wormhole open appears to require unusual stress energy, often described loosely as exotic matter, with properties that ordinary matter does not provide in the necessary form. Quantum theory allows limited negative energy effects in certain situations, but nothing remotely close to a demonstrated method for stabilizing a human-sized wormhole. There is also the problem of feedback. Once the mouths become separated in time, light or particles might be able to travel through the wormhole and loop through the surrounding space-time in ways that amplify quantum effects near the moment a usable time machine would form. Some calculations suggest this could destabilize the geometry before the connection becomes useful, although a complete theory of quantum gravity is still missing. So the honest answer is not that wormholes can connect us to the future, but that general relativity allows theoretical constructions in which two wormhole mouths become separated in time as well as space. If such a structure could somehow be created, stabilized, and kept open, you might step through a tunnel only meters long and emerge after an external world has lived through centuries. The deepest strangeness is that the wormhole would not be moving you forward in the ordinary sense. It would be connecting two clocks that no longer agree about when they are. And suddenly, the future would stop being a destination reached by waiting and become something far stranger. A place that might exist just beyond the other side of a doorway. Could moving one end of a wormhole turn it into a time machine? The most famous wormhole time machine idea begins with a surprisingly simple trick. Keep one entrance still, take the other on a relativistic journey, and bring it back younger than the first. Imagine two wormhole mouths, A and B, sitting beside one another with synchronized clocks. Now leave A on Earth and accelerate B to a speed extremely close to the speed of light. Send it on a long voyage, then return it. Because of special relativity, less time would pass for the traveling mouth than for the stationary one. From the outside, their clocks would now disagree. Perhaps 10 years passed beside A, while only 1 year passed beside B. Normally, that would simply be another version of the twin effect. But the wormhole adds a crucial ingredient. The mouths are still connected through the throat. In the idealized Morris Thorne-Yurtsever construction, the internal geometry can preserve a relationship between the mouths even after their external histories have diverged. That means entering one mouth could allow you to emerge from the other at an external time, different from the one you would reach by traveling normally through space. With a large enough time difference, a traveler could potentially pass through the wormhole and then move through ordinary space back toward the first mouth in such a way that they arrive before they originally departed. At that moment, the wormhole has become more than a shortcut. It has created a closed route through space-time. The same general idea does not even require rapid motion in principle. Placing one mouth in a stronger gravitational field than the other could also make their clocks age at different rates through gravitational time dilation. But there is an important limitation that science fiction often ignores. This kind of machine would not normally let you visit any arbitrary year in history. If the time offset was created only after the wormhole existed, you could not simply use it to travel to ancient Rome or the age of dinosaurs. The earliest accessible time would be tied to the period during which the mouths acquired their temporal separation. In other words, building the machine today would not automatically give you access to yesterday before the machine existed. Then come the much harder physical obstacles. No traversable wormhole has ever been found. Stabilizing one appears to require forms of negative energy that may be severely constrained by quantum physics. Accelerating a wormhole mouth while preserving the throat could introduce stresses that no known material or theory has shown can be managed. And as the configuration approaches the point where closed paths through time become possible, quantum fields may react violently enough to destabilize the wormhole. An idea related to Hawking's chronology protection conjecture. None of these objections has yet become a universal proof that wormhole time machines are impossible, but together they explain why the proposal remains theoretical rather than technological. Still, the logic is extraordinary because the mouth does not need to travel backward through time during its journey. It simply experiences less forward time than its partner. The paradoxical behavior appears only after the two mouths are reunited while remaining internally connected. You begin with two synchronized doors, send one on a journey through ordinary relativistic physics, and return with two doors that disagree about what time it is. If the throat still connects them, stepping through one might mean stepping not only across space, but across the disagreement between their clocks. And that disagreement is exactly where a hypothetical wormhole could begin to behave like a machine built from time itself. What would you see while traveling through a wormhole into the past? You might expect a journey through a wormhole to look like racing down a glowing tunnel, but real relativity gives no reason to expect anything resembling a cosmic hallway at all. A traversable wormhole is a hypothetical geometry of space-time, not necessarily a cylindrical passage floating through some larger space. So what your eyes would see would depend entirely on the wormhole's shape, gravitational field, motion, and the light entering both of its mouths. In the classic traversable wormhole models, the important requirement is that a traveler can cross the throat without encountering an event horizon or destructive singularity, meaning that light should also be capable of traveling through it. That immediately creates a remarkable visual consequence. Before you even enter, the mouth could act less like a dark hole and more like a distorted window onto another region of space-time. Photons arriving from the far side could travel through the throat and reach your eyes. So you might see scenery belonging to the other mouth while you are still standing beside the first one. But the image would probably not look like an ordinary window. Strong curvature bends the paths of light, and studies of wormhole gravitational lensing show that some wormhole geometries can produce highly distorted images, photon rings, and even multiple concentric images, as light takes different routes through the curved space-time. A star that physically lies behind you might appear in front of you because some of its light has passed through the wormhole. Parts of the distant sky could be magnified, stretched, duplicated, or wrapped around the apparent throat. Depending on the specific geometry, you might see several images of the same object formed by photons that circled the throat different numbers of times before reaching you. None of these effects gives us a universal picture of what a wormhole looks like, because there is no single experimentally confirmed wormhole metric describing a real object. Now add the time machine property. If the mouths have acquired a temporal offset, the light emerging from the far mouth could carry information from an external time different from the one surrounding you. You might therefore look through the opening and, in principle, receive photons from what your local clocks call the past before your body ever crosses the throat. The boundary between seeing another place and seeing another time would become strangely blurred. Motion of the mouths and differences in gravitational conditions could also shift the frequency and apparent brightness of incoming light, so the view might be redder, bluer, brighter, or dimmer depending on the exact setup, rather than obeying one cinematic rule. Then you enter. If the wormhole is genuinely traversable and its throat is short, there is no requirement that you spend minutes flying through a vast internal corridor. The proper distance through the throat could be much shorter than the ordinary distance between its mouths, and your crossing might take only a brief interval of your own time. You would continue seeing light throughout the journey, but the optical field could change rapidly as rays arriving from both external regions are bent around you. Instead of watching years rewind like a film, you might simply watch one distorted sky transform into another. Trees would not grow backward. People would not walk in reverse. Your heartbeat would not change direction. Once you emerged into the earlier external time, everything around you would behave locally forward, just as it always had. The only evidence that you had crossed into the past might be the date on a clock, the younger faces of people you remember, and the impossible knowledge inside your own mind. That may be the strangest scientifically defensible image of wormhole travel. Not a spectacular tunnel filled with reverse time, but a brief passage through violently distorted light, followed by an ordinary-looking world whose most impossible feature is simply that you have already lived through what has not yet happened there. Could two wormholes let you return before you left? Two wormholes arranged correctly could turn space-time into something resembling a causal circuit, allowing a theoretical traveler to complete an entire journey and reach the starting region at an external time earlier than departure. But the trick would lie in the time offsets between the mouths, not merely in owning two tunnels. Picture four wormhole mouths distributed through space. The first wormhole connects A to B, while the second connects C to D. Now imagine that relativistic motion or gravitational time dilation has caused the connected mouths to acquire carefully arranged differences in external time. Passing through A might deliver you from one date to a later or earlier date at B, while traveling a short ordinary distance from B to C and entering the second wormhole could produce another temporal shift at D. If those shifts add together in the right direction, the total route can close on itself. You leave the neighborhood of A at noon, cross the first wormhole, move through ordinary space, cross the second, and arrive back near your original location at 11:50. You have personally moved forward during every second of the journey, yet the complete route through space-time returns to an event lying before your departure. Physicists have studied exactly this broader type of construction. Goldworth, Perry, Piran, and Thorne analyzed a model time machine spacetime containing two temporal wormholes connecting regions at different times, with one wormhole carrying propagation in one temporal direction and the other providing the complementary connection. The resulting geometry contains a region with closed timelike curves. The crucial idea is therefore not that the second wormhole somehow undoes the first. Each leg of the trip is locally ordinary from the traveler's perspective. The paradoxical result appears only when you add all the legs together and discover that the route returns to its own causal past. It is similar to walking around a city block and returning to the same street corner, except that the geometry has folded time into the route along with space. There is also a useful condition hidden beneath the idea. The backward temporal shift provided by the wormhole network must exceed the ordinary forward time required to travel between the relevant mouths. If crossing one connection sends you 20 minutes backward, but reaching the next entrance requires an hour, you have gained nothing. You still arrive later overall. Only when the combined time displacement wins that race does a closed time-like path become possible. This makes two wormhole systems interesting because their mouths could, at least mathematically, be arranged into far more complicated causal networks than a single pair. A traveler could enter one connection, emerge into a shifted era, traverse another region, and use the second connection to complete the loop. Yet none of this means engineers could actually construct such a device. Traversable wormholes themselves remain hypothetical. Their stabilization appears to require highly unusual stress energy, and quantum effects near the formation of closed time-like curves may radically alter or destabilize the spacetime. Theoretical studies disagree on whether such chronology-violating geometries could survive once quantum physics is fully included, partly because we still lack a complete quantum theory of gravity. There is another subtlety. Two wormholes are not fundamentally required to create every conceivable time machine route. Even one suitably time-shifted wormhole, combined with an ordinary journey through external space, can generate a closed path in idealized models. What the second wormhole does is make the causal architecture richer, allowing both major legs of the route to exploit space-time shortcuts. And if such a network ever worked, the most disorienting moment might come after you finish the trip. Your watch could tell you that 20 minutes had passed. Your body would agree. Every thought would have followed the previous thought in perfect order. Yet you could stand beside the entrance, look across the room, and see your earlier self preparing to begin a journey you have already completed. Because nothing inside you traveled backward, while the path beneath you somehow curved far enough through space-time to bring your future back into contact with its own beginning. Could a black hole ever become a gateway through time? A black hole looks like the perfect place to hide a doorway through time. Yet the ordinary black holes described by general relativity behave much more like one-way boundaries than cosmic portals. The confusion begins because black holes and wormholes are mathematically related in some idealized solutions. In 1935, Einstein and Rosen described a geometry connecting two sheets of space-time through what later became known as an Einstein-Rosen bridge. That image sounds almost exactly like a tunnel waiting for a traveler. But the bridge associated with an ordinary eternal Schwarzschild black hole is not a stable passage through which you could enter one side and safely emerge from another. Modern numerical work on related Einstein-Rosen geometries likewise distinguishes such bridges from traversable wormholes. Horizons can form and make the connection non-traversable, If you fell toward a non-rotating black hole, the event horizon itself would not feel like a solid wall. For a sufficiently massive black hole, you might cross it without noticing a sudden local boundary at that exact instant. But once inside, the geometry changes the meaning of escape. Moving towards smaller radius becomes as unavoidable in your future as moving toward tomorrow is outside. Turning around with a stronger engine would not provide a route back through the horizon, because every future-directed path available to you remains directed deeper inward. The black hole can certainly alter your relationship with time before you cross it. Strong gravity can make your clock accumulate less time than clocks far away, allowing a form of one-way travel toward the distant future if you could approach and later escape without crossing the point of no return. But that is very different from using the black hole as a door into another century or into the past. Once you cross the horizon of an ordinary Schwarzschild black hole, classical general relativity gives you no path that returns you to the outside universe. And the famous second exterior region, drawn in the maximally extended mathematical diagram, should not be casually interpreted as another universe that an astronaut can simply visit. It belongs to an idealized eternal solution, not the straightforward history of a black hole formed from a collapsing star. This is the important difference between a map existing in the mathematics and a route being physically usable. General relativity can contain structures that look astonishing when drawn globally, but an astronaut must still follow a timelike path that remains physically available at every point. A normal black hole fails that test as a time gateway. It can separate your clock from the clocks of the distant universe. It can place regions of space-time permanently beyond communication. It can even reveal that space and time are far less rigid than human intuition suggests. But none of that gives you a tunnel through which you can choose an era and emerge again. So if you ever approached a silent black horizon hoping to find history folded behind it, the most sobering possibility is that the black hole really does lead you toward a radically different future, just not one from which you can return to tell anyone what you found. Could a rotating black hole contain paths into another time? Rotation changes a black hole so profoundly that, on paper, its interior contains regions stranger than anything hidden inside a non-spinning one. In 1963, Roy Kerr discovered the exact solution describing the space-time around a rotating mass, and the geometry now bearing his name remains the basic model for rotating black holes. Unlike the simpler Schwarzschild case, a Kerr black hole does not merely pull space-time inward. Its rotation drags space-time around with it, an effect known as frame dragging. Deep inside the idealized Kerr solution, the structure becomes even more extraordinary. There is an outer event horizon, but also an inner boundary called a Cauchy horizon, beyond which the ordinary ability to predict the future uniquely from earlier conditions begins to break down. Brandon Carter's analysis of the globally extended Kerr family showed just how complicated its causal structure becomes when the mathematical solution is continued beyond the regions visible from outside. In the fully extended geometry, one can encounter regions near the ring-shaped singularity where the distinction between space and time becomes twisted enough for closed time-like curves to appear, paths that, mathematically, can return an observer toward an earlier point in their own history. This is the origin of the seductive claim that a rotating black hole might act as a time machine. But the word might carries almost the entire weight of the idea. The perfect Kerr solution assumes an eternally stationary, exactly rotating black hole with none of the messy disturbances that real astrophysical objects experience. Real black holes are surrounded by radiation, infalling matter, gravitational waves, and perturbations, and the inner horizon appears to be extraordinarily sensitive to those disturbances. Numerical studies of perturbed Kerr interiors have found that radiation becomes violently amplified near the Cauchy horizon, driving curvature toward a singular behavior rather than leaving behind the smooth gateway suggested by the pristine mathematical extension. Even more recent nonlinear work published in 2026 strengthens this picture. finding curvature blow up and serious limits on extending realistic Kerr spacetime smoothly beyond the Cauchy horizon. In practical terms, the elegant map containing passages toward other regions or other times may be destroyed by the very instability generated when anything real tries to enter. There is also the ring singularity itself. It is sometimes portrayed as a harmless opening that you could fly through if you approached from the correct direction. But detailed work on Kerr-like geometries finds divergent tidal stresses near the singular set, making the idea of a spacecraft casually threading the ring physically dubious. This is a beautiful example of why exact mathematical solutions must be interpreted carefully. A map can contain a road that disappears the moment weather, traffic, and imperfections are added. The ideal Kerr geometry tells us that Einstein's equations are capable of arranging causality into astonishing forms. It does not tell us that nature lets astronauts survive those forms. If rotating black holes really do resemble Kerr black holes on the outside, and observations strongly motivate that model, their interiors may still erase the most exotic portions of the ideal solution through instability. So somewhere inside the mathematics of a spinning black hole, there are paths that seem to bend time back toward itself. But the universe may have hidden them behind not one barrier, but several, an event horizon you cannot escape, an unstable inner horizon, and a region where space-time itself may become singular before any traveler reaches the promised road into another time. Can general relativity really allow a path back into your own past? The unsettling answer is that Einstein's theory does not contain a simple rule saying your past must always remain unreachable. General relativity describes gravity not as a force pulling objects through a fixed arena, but as the geometry of space-time itself, and once space-time is allowed to curve, the possible paths through it become far stranger than ordinary experience suggests. Under normal conditions, your future always lies inside a region of space-time you can reach while moving slower than light, and your past remains behind you. Yet Einstein's equations are primarily local rules. They tell matter and energy how to curve space-time and tell objects how to move through that curvature, but they do not automatically guarantee that the global shape of every possible universe preserves a simple division between past and future. Physicists discovered this surprisingly early. Certain exact solutions of general relativity contain routes that eventually return a traveler to an event in their own causal past, while the traveler never locally exceeds the speed of light. The traveler's watch keeps moving forward, their body ages normally, and every nearby step looks physically ordinary. The impossibility appears only after examining the entire route and realizing that it bends around spacetime until later for the traveler meets. Earlier in the traveler's history, Kurt Gödel famously found a cosmological solution with this behavior in 1949, demonstrating that Einstein's equations alone do not guarantee a universal ordering of events. Other exact geometries developed later revealed similar causal structures under very different assumptions. This does not mean our actual universe contains roads back to yesterday. The known examples usually demand unusual global conditions, idealized matter distributions, extreme rotation, special space-time boundaries, or structures whose physical formation may be impossible. Observations also show that our cosmos does not resemble Gödel's rotating model in the way required for its most famous causal loops. The deeper lesson is mathematical rather than technological. Relativity permits more kinds of space-time than the universe appears to use around us. To understand why this happens, picture every event surrounded by a cone representing all the directions a slower-than-light traveler could move next. In familiar space-time, those cones are arranged so that following them forward can never bring you into your own past. But sufficiently unusual curvature can tilt and twist the allowed directions from place to place. A traveler always remains inside the locally permitted future direction. Yet after a long enough journey, the global geometry may carry that path back toward where it began in time. Nothing at one point announces that causality has broken. The strange result belongs to the shape of the entire space-time, And this is why general relativity leaves physicists with a profound distinction between what its equations allow and what nature can actually build. Quantum effects, stability problems, energy requirements, or deeper laws of quantum gravity may ultimately eliminate every realistic route into the past. We do not yet know, but Einstein's theory already taught us something more disturbing than a functioning time machine. The familiar belief that time must always form one clean, irreversible road is not written into the basic geometry of gravity as strongly as human intuition once assumed. What is a closed time-like curve, and why does physics allow it? There is a path you could theoretically follow by moving forward every second of your life, and still end up arriving before you began, and physicists have a precise name for it: a closed time-like curve. The phrase sounds technical, but its meaning is surprisingly simple once you separate three ideas. Timelike means the path can be followed by something with mass moving locally slower than light, such as a person, spacecraft, or clock. Curve means it is a route through space-time rather than merely through space. And closed means that the route eventually returns to the same space-time event, or at least to the causal past of an earlier portion of the journey. The astonishing point is that the traveler never needs to feel time reversing. Imagine carrying a clock along the entire path. It keeps ticking in one direction. Your memories continue forming, your cells continue aging, and each next step remains inside your local future. Yet space-time itself has been curved so strangely that this sequence of perfectly ordinary local steps forms a loop when viewed globally. This is very different from watching the universe run backward like a reversed film. A closed time-like curve is not ordinary motion with a negative clock. It is a forward-moving life following a geometry whose future eventually reconnects with its own past. Why would physics tolerate something so counterintuitive? Because general relativity places strong restrictions on local motion, but fewer automatic restrictions on the global topology and causal structure of an entire spacetime. Einstein's equations relate curvature to matter and energy, but they do not contain a universal commandment saying every physically allowed solution must possess one global surface that can be called now, and from which the entire future develops uniquely. Spacetimes that do possess such well-behaved surfaces are called globally hyperbolic, and they are especially comfortable for physics, because you can specify conditions on one complete slice and predict what happens later. A spacetime containing a closed time-like curve cannot behave that simply. Somewhere the causal structure folds back, and the neat distinction between initial conditions and future consequences begins to fail. This is one reason closed time-like curves are so important, even if nobody ever builds a time machine. They test the foundations of what physicists mean by prediction. If information can return to an earlier event, then knowing the state of a system at one moment may no longer be enough to determine everything independently of conditions elsewhere around the loop. The full history may need to fit together at once, but allowed by an equation is not the same as realizable in nature. Some solutions containing closed time-like curves rely on idealizations that may never arise from realistic initial conditions. Others develop unstable horizons, require exotic distributions of energy, or lead into regimes where classical relativity can no longer be trusted without quantum gravity. So when physicists say general relativity permits closed time-like curves, they are not announcing that time machines exist. They are pointing to a gap between local causality and global geometry. Locally, every traveler can obey the speed of light and move toward what feels like the future. Globally, the spacetime may still arrange those allowed futures into a circle. And that is what makes the idea so difficult to forget. A closed time-like curve does not break the rules at any single step. It reveals that perfectly legal steps can sometimes form a path whose final destination forces you to question what future and past meant in the first place. Could a rotating universe make time travel possible? Imagine discovering that the universe itself is slowly turning, not like a planet spinning inside space, but with space-time arranged so that the rotation is built into the geometry of the cosmos. This is not how our observable universe appears to behave, but general relativity allows a remarkable theoretical example known as the Gödel universe, introduced by mathematician Kurt Gödel in 1949. In that model, matter fills the universe while the entire cosmic geometry has a kind of global rotation, and the consequence is extraordinary. The light cones that normally define which directions lead into the future become tilted more and more as you travel across large distances. If the rotation is strong enough, a path that always moves locally forward in time can eventually bend around the universe and return to an event in its own past. You would never need to exceed the speed of light. Your watch would continue ticking normally, and each moment along the journey would feel like an ordinary future moment. Yet the global geometry would carry you around a vast loop until the place you finally reach lies earlier than the moment you left. This is one of the clearest demonstrations that general relativity does not automatically protect the familiar idea of one universal sequence of past, present, and future. But there is an equally important scientific reality. Gödel's universe is almost certainly not our universe. A globally rotating cosmos would leave observational signatures in the large-scale distribution of matter and in the cosmic microwave background, and modern measurements strongly constrain any such cosmic rotation to be extremely small. The universe we observe is instead remarkably close, on large scales, to the expanding cosmological models used in standard modern cosmology, without the kind of global rotation required for Gödel's closed time paths. The model also contains features that make it very unlike our cosmos, including no ordinary cosmic expansion of the kind we measure today. So the rotating universe time machine is not a hidden route astronomers expect us to discover somewhere beyond the Milky Way. It is a lesson about the freedom built into Einstein's equations. Gravity is geometry, and geometry can be arranged in ways that seem impossible from the perspective of everyday life. A sufficiently rotating space-time can tilt every traveler's local future little by little until the future eventually points back toward what another part of the universe calls the past. And that creates a deeply unsettling thought. Perhaps the separation between yesterday and tomorrow is not protected by some universal wall, but by the particular structure of the cosmos we happen to inhabit. In another mathematically possible universe, time might not stretch outward like an endless road. It could curve around on scales so vast that a traveler who never once turns back could eventually arrive at the beginning of their own journey. Our universe appears to spare us that possibility, but Gödel's solution remains a quiet reminder that the direction of time is not guaranteed merely by intuition. It depends on the geometry of everything. Could cosmic strings bend space enough to create a time machine? A time machine might not need a wormhole or a black hole at all. In one famous theoretical proposal, two unimaginably thin defects left over from the early universe could distort space-time enough to create a path into the past. These hypothetical objects are called cosmic strings. They are not ordinary strings made of matter, but possible topological defects that could have formed during symmetry-breaking transitions when the early universe cooled. If they exist, they may be extraordinarily thin while carrying enormous mass energy per unit length, so their gravitational effect would be unlike that of a star or planet. Instead of pulling space inward in the familiar way, an ideal straight cosmic string creates what is called a conical geometry. Locally, space-time can remain relatively flat, but globally it behaves as though a narrow wedge has been removed and the edges sewn together. Travel around the string and geometry does not quite add up the way ordinary flat space does. This peculiar structure inspired physicist J. Richard Gott to propose in 1991 that two long cosmic strings moving past one another at very high speed could, under special conditions, produce closed timelike curves. The idea is not that the strings open a glowing portal. Their combined motion and space-time distortion could change the possible routes between events so dramatically that a traveler moving through the surrounding space might complete a journey and arrive before departure according to the external frame. Every local part of the trip could remain slower than light, yet the overall geometry would provide a shortcut through causality itself. That sounds like an elegant escape from the engineering nightmare of constructing a wormhole, but the proposal quickly runs into severe physical difficulties. First, no cosmic string has ever been confirmed observationally. Searches using gravitational lensing, gravitational waves, and the cosmic microwave background have placed increasingly strong limits on how common or massive such strings could be. Second, the GOT time machine configuration requires extremely specific motion and geometry. The strings must move past one another at extraordinarily high relative speeds. And later, analyses showed that creating the needed causal structure from physically reasonable initial conditions is far more difficult than simply placing two strings together. Work by Deser, Jacques, and 't Hooft demonstrated that in the simplified two-string system, the conditions associated with GOT's closed causal paths lead to serious global constraints. While further studies of causality suggested that realistic, isolated configurations may not allow the machine to be constructed from ordinary initial states in the way the original picture might suggest. The deeper difficulty is that a mathematical space-time containing closed loops is not the same thing as a machine you can assemble inside an already ordinary universe. Global geometry matters. You cannot always take a strange solution, cut out the useful part, and manufacture it locally without changing the rest of space-time in ways the equations refuse to permit. Cosmic strings therefore sit in a fascinating middle ground. Unlike completely invented science fiction devices, they arise naturally in some theories of high-energy physics, and their gravitational behavior is serious theoretical physics. Yet neither the strings themselves nor the time machine arrangement has been observed. If cosmic strings do exist, they could still reveal spectacular phenomena such as distinctive gravitational lensing or bursts of gravitational radiation without ever permitting a traveler to reach yesterday. And perhaps that is what makes the idea so compelling. You begin with something thinner than an atom, yet potentially stretching across cosmic distances. Add motion fast enough to twist the relationship between space and time, and discover that relativity once again comes dangerously close to allowing a route backward. But every time physics seems to open that door, another question appears beside it. Not whether space-time can be bent into a paradox on paper, but whether the real universe will ever let you arrange the pieces strongly enough to walk through. Could an infinitely rotating cylinder let you travel into the past? The famous infinite rotating cylinder time machine hides an important detail in its name. The cylinder does not need infinite rotational speed. The truly impossible ingredient is that, in the idealized solution, it stretches infinitely far. In 1936, Willem van Stockum found an exact solution to Einstein's equations describing rapidly rotating cylindrical matter, and decades later Frank Tipler showed that the geometry associated with an infinitely long, sufficiently fast rotating cylinder could contain closed timelike paths, meaning trajectories that return toward their own past. The reason is not that rotation somehow makes clocks literally run backward. A massive rotating object drags the surrounding space-time with it, an effect related to frame dragging. Around an extreme cylinder, that dragging can become so strong in the mathematical model that the directions normally identified as future tilt progressively around the cylinder. A traveler circling through the right region could always move locally forward according to their own clock, never needing to exceed the speed of light, yet eventually follow the twisted causal geometry into an event earlier than departure. That is the extraordinary part. You would not reverse your heartbeat, watch stars retrace their motion, or feel yourself moving backward. You would keep experiencing one second after another while the shape of space-time turned your forward path into a loop. But the construction becomes far less magical once you ask what you would actually have to build. Infinite length is not a decorative assumption. It removes the ends of the cylinder and gives the surrounding gravitational field a global structure that no finite laboratory object can reproduce exactly. Tipler's original paper suggested that a finite cylinder might also act as a time machine, but that suggestion was not a demonstration that an ordinary finite machine could simply be constructed from realistic matter. A real cylinder would have ends, structural stresses, limited density, finite energy, and matter that must obey the laws governing actual materials. Spinning anything massive enough and fast enough to produce extreme frame dragging would create extraordinary mechanical demands long before you could casually climb into a spacecraft and orbit it. And there is a deeper distinction that appears repeatedly in Relativity. Finding a space-time geometry containing closed time-like curves is not the same as showing that such a geometry can evolve from reasonable initial conditions inside our universe. Later work on proposed time machine geometries has repeatedly found restrictions on constructing causality-violating regions from ordinary starting states, even though general relativity itself admits many exact solutions containing them. So the tippler cylinder should not be described as a forgotten blueprint waiting for stronger steel. It is something more intellectually valuable, an example showing that rotation can twist spacetime so severely, at least in ideal mathematics, that the distinction between going around an object and going backward in time becomes unexpectedly fragile. You begin with something familiar, a cylinder spinning around an axis, and push Einstein's gravity beyond any environment humanity has ever created. Eventually, the geometry stops behaving like the space around a machine and begins behaving like a trap laid across causality itself. Yet the very assumption that makes the trap possible also pushes it away from physical reality. The cylinder teaches you that Einstein's equations can imagine a road into yesterday, while nature may answer with a quieter condition. Perhaps the road works only when the machine is so impossibly large that no traveler could ever finish building its first end. Why might every real-time machine destroy itself before it works? Time machine could fail at the exact instant it becomes capable of reaching the past, not because someone sabotages it, but because its own geometry may amplify quantum effects until the machine can no longer remain the thing you built. This is the central intuition behind Stephen Hawking's chronology protection conjecture. Proposed in 1992, perhaps the laws of physics prevent closed time-like curves from forming in physically realistic situations, protecting cause and effect before macroscopic travelers ever get the chance to violate them. To understand why, imagine gradually modifying some hypothetical device, a wormhole, rotating geometry, or another extreme configuration, until space-time is almost capable of sending a light ray back to where it began. Before actual time travel becomes possible, there can appear a boundary known as a chronology horizon, separating the ordinary causal region from the region where closed causal paths are about to form. Near that boundary, something unusual can happen to quantum fields. Empty space in quantum field theory is not literally empty. Fields remain present even when there are no ordinary particles. If light or field disturbances can travel around paths that become almost closed, they may return again and again through nearly the same region. In several models, this repeated propagation produces enormous vacuum polarization effects near the would-be chronology horizon. Calculations by Klinkhammer found divergences associated with closed null paths in a generic class of compactly generated chronology horizons, supporting the idea that the stress carried by quantum fields could become violently large precisely where causality begins to fail. Gravity then turns this from a mathematical inconvenience into a possible self-destruction mechanism, because energy and stress themselves curve spacetime. If the quantum field becomes sufficiently intense, its gravitational back reaction could alter the carefully prepared geometry, closing the wormhole, destroying the chronology horizon, or otherwise preventing the causal loop from completing. The machine would approach the threshold, quantum effects would grow, the geometry would respond, and the doorway into the past could disappear before it ever fully opens. Later mathematical work made the situation even more subtle. Kay, Radzikovsky, and Wald showed that for spacetimes with compactly generated Cauchy horizons, ordinary quantum field theory develops unavoidable singular or ill-defined behavior at certain points on the horizon. Familiar quantities such as the renormalized stress energy cannot simply be assumed to remain well-behaved there. That does not mean physicists have proved that every conceivable time machine explodes. There are proposed geometries for which the usual divergence arguments behave differently, and researchers have constructed counterexamples and alternative scenarios questioning whether one universal, semi-classical protection mechanism works in every case. Most importantly, the very place where the problem becomes extreme may require a full theory of quantum gravity, something physics still does not possess experimentally, so chronology protection remains a conjecture, not a final law. Yet it offers one of the most elegant possibilities in the entire time travel problem. Nature may not need mysterious coincidences to prevent paradoxes, and it may not need to decide what happens after you arrive in the past. The prohibition could happen earlier, automatically, through the interaction of quantum fields and curved spacetime. Every machine might work beautifully, while it is merely almost a time machine. Its clocks synchronize, its fields remain stable, its geometry approaches the required configuration. Then, as the final causal route begins to close, the same spacetime that was supposed to carry you backward could generate the disturbance that tears the route apart. The universe would allow you to build 99.9% of a doorway into yesterday and reserve the final fraction for physics strong enough to make sure the door never opens. Could quantum physics prevent time travel paradoxes automatically? What if a time machine never needed to stop you from creating a paradox because quantum physics simply refused to assign the contradictory outcome a valid state in the first place? This is very different from the idea that a wormhole collapses before you use it, or that some mysterious force makes your plans fail. Instead, several theoretical models ask whether quantum mechanics itself could make a journey through a closed path in time internally consistent. One of the best-known approaches was proposed by physicist David Deutsch in 1991. Imagine that a quantum system enters a region of space-time, travels around a hypothetical closed timelike curve, and returns to interact with an earlier system. The obvious danger is that the interaction might change the returning system in such a way that it could never have entered the loop in the state required to produce that change. Deutsch approached this by requiring the quantum state circulating through the loop to be self-consistent. After completing the interaction, the state must match the state that entered the closed portion of the process. Remarkably, quantum mechanics can sometimes satisfy this requirement by allowing a mixed state rather than forcing the system into one simple classical alternative. In a classical story, you might have only two possibilities, each destroying the conditions required for itself. In the Deutsch model, the quantum description can settle into a state that remains consistent around the entire loop, avoiding the direct contradiction. But this is not the only proposed solution. Another framework developed by Seth Lloyd and collaborators uses quantum teleportation together with post-selection. Here the basic idea is different. Among the possible quantum outcomes, only those compatible with the required time loop boundary conditions are retained. An impossible history effectively receives no successful outcome in the model. The researchers even performed laboratory experiments reproducing the mathematical consistency behavior using ordinary quantum systems. But nothing in those experiments actually traveled into the past. They simulated what the proposed theory predicts if closed timelike curves existed. That distinction is crucial. Quantum physics has not demonstrated that nature automatically solves real time travel paradoxes, because no physical closed timelike curve has ever been observed. Even more importantly, the Deutsch and post-selected approaches are not equivalent. They can predict different behavior, which tells you that physicists do not yet know what quantum mechanics would actually do in a real region where causality loops back on itself. The question remains active even now. Work published in 2026 studies how information could behave in noisy, post-selected, closed time-like curve channels. But this remains theoretical quantum information research, not evidence that messages are being sent into yesterday. Still, these models reveal something profound. Classical paradoxes usually arise because you imagine reality being forced to choose one definite history that then destroys itself. Quantum mechanics already teaches us that microscopic systems do not always fit into such simple either-or descriptions. Perhaps if space-time ever allowed a causal loop, nature would not need to repair the contradiction afterward. The allowed quantum state might already be restricted by the requirement that the complete loop makes sense. You would experience events one by one, never seeing an invisible hand correcting them, while beneath that ordinary sequence, the quantum state of the system satisfies conditions connecting what you call the future with what you call the past. Yet we should resist turning this elegance into certainty. These theories may be clues, approximations, or mathematical curiosities that disappear once gravity and quantum mechanics are finally unified. What they show is not that quantum physics has solved time travel, but something almost as interesting. When you force our best theories to confront a history that curves back onto itself, quantum mechanics possesses ways of describing consistency that classical intuition never imagined. Perhaps paradoxes would not be dramatic catastrophes waiting at the end of a time machine. Perhaps they would be possibilities that the deepest rules of nature never allow to become physically complete. Can a quantum particle interact with its own past? Picture a single quantum particle arriving in a laboratory and encountering another state that is not its twin, not a clone, and not a second particle produced beside it, but an older version of the very quantum information it will carry later. That bizarre interaction is genuinely studied in theoretical physics, although no experiment has ever sent a particle into its own past. In a closed timelike curve model, the idea can be represented surprisingly clearly. A quantum system moves normally forward, reaches an interaction point, and eventually enters the hypothetical time loop. The loop returns its state to an earlier stage of the experiment, where that older state can interact with the younger system before the younger system has entered the loop. You now have something impossible in ordinary laboratory causality. The state produced later participates in determining the state that will eventually produce it. Deutsch's model formalizes this by treating a normally evolving quantum system as interacting with another quantum state confined to the closed timelike curve. The circulating state must come out of the interaction in a form consistent with the state that went into the loop. This sounds impossibly abstract until you realize that physicists have simulated the mathematics in the laboratory. In 2014, Martin Ringbauer and colleagues built a quantum optical experiment that reproduced the non-linear behavior predicted for a qubit interacting with an older version of itself in the Deutsch model. Again, no photon actually traveled through time. The researchers constructed an ordinary quantum circuit whose relationships reproduce the equations of the hypothetical interaction. That allowed them to investigate what the theory would predict without claiming to have created a space-time loop. The simulated system displayed consequences that are far stranger than simply seeing a particle collide with itself. Under the Deutsch model, access to a closed timelike curve changes the effective rules governing quantum information. The experiment explored predictions including the ability to distinguish certain quantum states that ordinary quantum mechanics does not allow you to distinguish perfectly. This happens because the self-consistency requirement makes the effective evolution non-linear, meaning the output does not behave like an ordinary isolated quantum system evolving through familiar quantum operations. That should immediately make you cautious. These exotic abilities are not known properties of real particles. They are consequences of adding a hypothetical closed timelike curve to quantum mechanics. Another proposed theory, the post-selected model, handles the same basic situation differently and produces different predictions. So even the mathematics does not give us one universally accepted picture of what a particle meeting its own past would do. Yet the thought experiment reveals why quantum time travel is so conceptually powerful. In ordinary physics, you prepare a particle, let it evolve, measure what happens, and place those events into a clean sequence. Here the sequence folds. The state you measure later helps determine an interaction that occurs earlier, while that earlier interaction helps produce the later state. There may be no meaningful way to isolate one direction and call it the complete cause. The particle is not literally thinking backward or remembering its future. Its quantum state is simply being required to satisfy relationships across a causal loop that does not exist in ordinary spacetime. And if such loops were ever physically possible, the familiar question, what state was the particle in before the interaction, might stop having the simple answer you expect, because part of the condition defining that earlier state could come from what happens later. For now, every laboratory demonstration remains a simulation of these rules, rather than evidence of backward time travel. But the simulations serve a serious purpose. They let physicists test the logical consequences of combining quantum information with space-time structures permitted mathematically by general relativity. And perhaps that is the most unsettling thing the particle teaches you. It does not need consciousness, intention, or a memory of tomorrow to challenge causality. If space-time ever curved the right way, something as small and silent as a quantum state could be forced into a conversation with its own history, where the answer returning from the future becomes part of the question that created it. Could quantum time travel produce several outcomes at once? The strangest version of quantum time travel may not force history to choose a single answer immediately, because quantum theory already knows how to describe several alternative possibilities before any observer experiences a definite result. But this needs to be understood very carefully. A quantum superposition is not simply a collection of ordinary events all happening side by side, like scenes playing on different television screens. It is a single quantum state containing alternative possibilities, whose probability amplitudes can interfere with one another. In ordinary quantum experiments, those alternatives can remain coherent until interaction with a measuring device or the surrounding environment makes them effectively distinguishable. If you introduce hypothetical time loops into this framework, the question becomes much stranger. Could the complete quantum history contain several internally compatible ways for an event to happen rather than one classical sequence? Some theoretical approaches to closed timelike curves allow quantum states that cannot be interpreted as one clean classical history circulating around the loop, while other formulations select only outcomes compatible with particular consistency conditions. These approaches do not all agree, and no experiment has demonstrated a real closed timelike curve, so physics cannot honestly say that a time traveler would literally experience several futures at once. What we can say is that quantum mechanics already has a language for alternatives that remain physically meaningful before they are reduced to a classical record. Researchers have even developed an entangled histories framework in which different sequences of a quantum system's states across several times can be combined in a way analogous to entanglement between separate systems. Experiments with single photons have prepared and tested such multi-time history states, showing that quantum alternatives associated with different times can possess correlations that cannot be represented as one simple classical trajectory. None of those experiments involve sending anything into the past. They are important precisely because they separate two ideas that fiction often mixes together. Quantum histories can be non-classical even when time itself behaves normally. Now imagine adding a genuine space-time loop, if nature permitted one. A particle approaching the loop might not have to follow one sharply defined classical story from the beginning. Several possible sequences of interactions could contribute to the quantum state, and only the complete physical process would determine what can finally be observed. Yet even then, an observer would not necessarily wake up remembering several contradictory lives. In standard quantum experiments, measurements produce definite recorded outcomes for the observer, while the underlying theory assigns amplitudes to alternatives before that record becomes established. Whether a deeper interpretation says all branches remain real is a philosophical interpretation of quantum mechanics, not an experimentally settled fact. There is another complication. Temporal quantum correlations differ from spatial ones, because an earlier operation can physically influence a later measurement, whereas the later setting cannot ordinarily send information backward to alter the earlier event. Researchers have shown that some multi-time quantum correlations are genuinely non-classical, but their causal structure is not the same as ordinary spatial entanglement. So the scientifically interesting possibility is not a traveler watching 5 versions of history happen simultaneously like a supernatural vision. It is that, if quantum theory ever had to describe a real-time loop, the underlying state might resist being reduced to one simple classical sequence until the entire loop is treated consistently. Several possible histories could contribute to what happens without each one becoming a separate conscious experience. And that leaves you with a deeper question than the usual paradox. Perhaps time travel would not force reality to choose between one past and another at the beginning of the journey. Perhaps at the quantum level, the very idea that history must have only one sharply defined route before observation is already too classical a way to think about time. Can entanglement connect events across different times? 2 quantum events can be linked across time in ways that look surprisingly similar to entanglement across space, but that does not mean the future can secretly reach backward and rewrite the past. Ordinary entanglement is usually introduced with 2 particles created together and then separated. Measurements on them reveal correlations stronger than classical local theories can explain, even when the particles are far apart. But time introduces another possibility. Instead of comparing 2 different systems at 2 different places, physicists can study one quantum system at several different moments and ask whether the sequence of events can be described by an ordinary classical history. Experiments have shown that the answer can be no. A single photon can be prepared, manipulated, and measured at several times in ways that produce genuinely non-classical multi-time correlations. In one line of work, researchers developed a unified description of spatial and temporal quantum correlations and experimentally examined processes where measurements on the same quantum system at different times behave in ways closely related to correlations normally associated with multipartite quantum systems. Another experiment used a single photon to study multi-time quantum correlations within the Page-Wooter's approach to time, demonstrating correlations between clock information and the evolving system, while the global state could be described differently from the internal observer's perspective. Even more strikingly, researchers have experimentally prepared what they call entangled history states, where the polarization states associated with one photon at 3 different times form a mathematical structure analogous to a 3-part quantum entangled state. This sounds dangerously close to saying the same particle is entangled with its own past, but the wording needs care. Temporal correlations are not identical to ordinary entanglement between independent particles. Measurements made at an earlier time can physically disturb the system and influence what happens later. That direct causal influence does not exist between space-like separated measurements in an ordinary Bell experiment. Because of this asymmetry, physicists have had to develop special tests and definitions for what counts as genuinely non-classical correlation through time. There is also something called time bin entanglement, where photons are placed into coherent superpositions associated with early and late time windows. Experiments can entangle those temporal modes and even preserve them in quantum memories. But again, this does not mean a photon in the future is sending instructions to its own past. It means that the quantum state contains correlations involving distinguishable temporal modes, and the correlations become visible when the appropriate interference measurements are performed. The difference matters enormously. Entanglement is a statement about the structure of a quantum state and the statistics of measurements. It is not automatically a communication channel. Even spatial entanglement cannot be used by itself to send controllable messages faster than light. And temporal quantum correlations do not provide experimental evidence for messages traveling backward in time. What they reveal is more subtle. Quantum mechanics does not always allow you to describe a system as possessing one independent state at each moment, with each moment connected to the next only through an ordinary classical story. Sometimes the physically meaningful object is the pattern of correlations across several times. The past measurement, the intermediate evolution, and the later measurement can belong to one quantum description whose structure cannot be reduced to a collection of separate snapshots. And perhaps that is the deeper lesson. You normally imagine time as a shelf filled with isolated moments, each one becoming real and then disappearing before the next arrives. Quantum experiments suggest that, at least for carefully controlled microscopic systems, nature can preserve relationships across those moments in a way that makes the full history more fundamental than any single frame. The events remain ordered, the future does not send a usable message backward, and causality has not been overthrown. Yet the quantum system seems to remember its journey not as a sequence of disconnected instants, but as one pattern stretched quietly across time. Could faster-than-light communication send a message into the past? A message that outruns light may do something far stranger than arrive quickly. Under the right conditions, another observer could describe it as arriving before it was sent. The reason comes from special relativity, where space and time are not separate universal backgrounds, and observers moving relative to one another can disagree about the timing of events that are too far apart for an ordinary light signal to connect them. For events joined by slower than light or light speed communication, this disagreement never reverses cause and effect. Everyone agrees that the emission comes before the reception, but if controllable information could cross the distance faster than light, the two events would be separated in a different way, what physicists call space-like separation, and their time ordering can depend on the observer's motion. In one reference frame, you send the message first and someone receives it later. In another moving frame, the reception can be assigned an earlier time than the emission. This alone does not automatically create a usable time machine, because changing the order assigned by coordinates is not yet the same as physically sending information back to your own earlier self. The real trouble begins if the receiver can send a second superluminal reply under suitable conditions. Imagine Earth and a rapidly moving spacecraft passing one another. Earth sends an instantaneously fast, or simply sufficiently superluminal message toward the spacecraft. Because the spacecraft has a different division of space and time, it can receive the message and immediately transmit a superluminal response. When that second signal is transformed back into Earth's reference frame, certain combinations of relative motion and signal speed can make the reply reach Earth before Earth transmitted the original message. This is the basic logic behind the famous tachyonic anti-telephone thought experiment. Special relativity therefore creates a deep connection between unrestricted faster-than-light signaling and causal loops, although the connection depends on assumptions about how the hypothetical superluminal signal propagates. Research has emphasized that faster-than-light motion by itself does not logically force time travel in every conceivable theory. A preferred frame, restrictions on propagation, or other new physical rules could potentially prevent the return leg needed to form the loop. That qualification matters because popular explanations often jump from faster than light directly to you can message yesterday. The dangerous ingredient is controllable. Superluminal causation combined with a relativistic structure allowing observers in relative motion to construct the right sequence of exchanges. Modern work on relativistic causality likewise distinguishes superluminal signaling from broader notions of superluminal causal influence, and shows that the relationship between such influences and causal loops is subtler than one simple slogan suggests. And nothing humans have actually observed provides this ability. Experiments in specially engineered optical media have produced pulse peaks or group velocities that appear superluminal or even negative. But careful analysis shows that this does not provide usable information traveling faster than light. Quantum noise and the behavior of the signal front preserve causal communication. Entanglement does not rescue the idea either, because its correlations cannot be controlled to transmit an arbitrary message beyond the ordinary causal limit. So the scientifically responsible answer is conditional but extraordinary. If nature allowed the right kind of freely controllable, faster-than-light communication while preserving the relevant symmetry of special relativity, then arrangements can be constructed in which a message returns to the sender's own past. The speed of light is therefore more than a cosmic speed limit. It helps protect the ordering of causes and effects. Break that limit in the wrong way, and the first thing you might lose is not distance, but the guarantee that the message you are reading had to be sent before you received it. Could you receive an answer before you send the question? At 9:59, you find a message on your screen saying, "The answer is Paris." And only at 10:00 do you decide to type the question, "What is the capital of France?" A harmless example that hides one of the most dangerous structures causality can contain. Receiving an answer before asking its question is stronger than simply having two observers disagree about which distant event happened first. To make the effect meaningful for you, information must complete a causal route that returns to an earlier point in your own history. Ordinary relativity prevents this with light speed and slower communication. Although different observers can disagree about how much time separates distant events, no observer can send a normal reply around a sequence of causal signals and have it arrive before the original request. The future light cone keeps the chain ordered. A hypothetical faster-than-light exchange can change that geometry. If two observers are moving relative to one another, and both can use an appropriate superluminal channel, one can send a question, the other can receive it and return an answer. And the combined route can, in idealized constructions, place the returning answer in the first observer's past. That final step is what converts a strange coordinate effect into a genuine causal loop. The answer is now physically available before the action that supposedly caused it. Special relativity has long been used to analyze such tachyonic anti-telephone scenarios, although researchers have also shown that whether a specific faster-than-light theory actually permits the loop depends on additional rules governing the hypothetical signals. Now make the example more serious. At 9:59, you receive a long random number. At 10:01, you are supposed to generate a random number and send it to the future recipient, who sends the same number back to 9:59. Where did that particular sequence of digits originate? You copied it because you received it, while the recipient returned it because you later sent it. The information can become trapped inside a causal circle with no obvious first act of generation. Worse, you can deliberately challenge the loop. After receiving Paris at 9:59, you promise yourself that at 10 hours you will ask a question whose answer is definitely not Paris. Now the system seems to demand mutually incompatible events. If the answer arrives, you change the question. If you change the question, that answer should not have arrived. This is why communication into the past is not merely a clever way of knowing tomorrow's lottery numbers. It attacks the ordinary experimental logic on which prediction itself depends. Scientists assume that an intervention performed now can influence later observations without those later observations reaching backward and changing which intervention was chosen. Modern research distinguishes several notions of causality and has even shown mathematically that causal loops and signaling constraints must be treated carefully rather than assumed to be identical concepts. None of this means anyone has received an answer from tomorrow. Relativistic quantum field theory is constructed to respect causal signaling, and physically local measurement interactions do not provide a loophole for sending controllable information outside the allowed causal structure. The scenario is therefore a test of what our theories would have to surrender if backward communication became possible. And perhaps the strangest consequence is not knowing the future before everyone else. It is losing the ordinary meaning of a question. A question normally exists first, creates a request for information, and eventually receives an answer. Close that causal chain through time, and the answer can become part of the reason you ask. Push it further, and you may no longer be able to point to a first moment when the conversation began. You would sit at your desk staring at words that seem to know what you are about to type, while physics confronts a far deeper problem than prediction, whether cause and effect can still be separated when the reply is already waiting. What happens to cause and effect if time travel becomes possible? Cause and effect would not simply disappear if time travel became possible. Something far stranger could happen instead. The universe might preserve causality in every small neighborhood, while losing the ability to arrange all causes and effects into one clean global order. In ordinary life, causality forms a structure so familiar that you rarely notice it. A match is struck before the flame appears. A star emits light before a telescope receives it. A neuron fires before the muscle it controls contracts. You can keep tracing these connections backward, building a chain in which causes precede their consequences. And because ordinary space-time contains no route back into your own causal past, those chains do not normally close into circles. This ordering is one of the foundations of prediction. Physicists specify what a system is like at an earlier time, apply physical laws, and calculate what can happen later. But a space-time containing genuine closed timelike curves changes the architecture of that reasoning. General relativity contains mathematical solutions in which a future-directed traveler can eventually return to an earlier event, creating a causal chain whose later stages can influence its earlier stages. Imagine a sequence with 4 events. You perform A, which produces B. B eventually leads to C. C sends a traveler into the past, where the traveler performs D, but D influences A. There is now no clean first link. Every event can still have a nearby physical explanation. Switches activate because hands press them. Machines respond because currents flow. People move because muscles contract. Locally, nothing needs to happen without a cause. The strange feature appears only when you step back and examine the complete chain. A helps cause B, B helps cause C, C helps cause D, and D helps cause A. Cause and effect have formed a circle. That would radically change what it means to explain an event. In ordinary reasoning, you expect explanation to eventually point toward earlier conditions. Inside a causal loop, asking for the earliest cause may be meaningless because there may be no earliest member of the loop. Yet this does not automatically mean that anything could happen. Some theoretical approaches require the complete history to obey consistency conditions, so events around the loop must fit together rather than producing mutually impossible states. Other quantum frameworks explore situations where even the order between processes can become less definite than ordinary classical causality suggests. Research on indefinite causal order shows that quantum theory can formally describe processes for which assigning one fixed order to certain operations is not always appropriate, although such laboratory frameworks are not evidence of macroscopic time travel. The most profound change would therefore be to prediction itself. If future events can participate in determining earlier conditions, knowing everything about one moment may no longer let you treat the rest of history as a simple calculation marching forward. The complete arrangement may need to satisfy conditions distributed around the entire loop. You could know what happens tomorrow partly because tomorrow depends on something you do today, while what you do today partly depends on information that comes from tomorrow. The familiar distinction between explaining an event from its past and constraining it by its future would begin to blur. Still, no experiment has shown that our universe contains a traversable closed time-like curve, and the physical mechanisms proposed for creating them face severe difficulties. So time travel has not forced science to abandon causality, but the equations teach an unsettling lesson about what causality really is. Perhaps cause and effect are not protected because time itself possesses a sacred forward direction. Perhaps they remain orderly around us because the geometry of our actual space-time prevents causal chains from bending far enough to bite their own tails. If that geometry ever changed, you might still understand every individual event perfectly, and yet be unable to answer the simplest question of all. Which event truly came first? Could an effect exist before its cause? Before calling something an effect that happened before its cause, you first have to ask a surprisingly difficult question. What does before actually mean in physics? Special relativity already teaches that distant observers can disagree about the order of certain events. If two events are separated so that no light speed or slower signal can travel from one to the other, one observer can assign event A first, while another moving observer assigns event B first. But this is not retrocausality. Neither event can be the ordinary controllable cause of the other, so no observer watches a genuine consequence occur before the physical process that generated it. Causal order remains protected for events that can actually exchange normal signals. A true effect before cause situation would require something stronger. Information or influence at a later event would have to participate in determining an earlier one. Physicists and philosophers have seriously investigated models with exactly this feature, especially in the foundations of quantum mechanics, where they are usually called retrocausal or time-symmetric approaches. In some of these models, both earlier preparation conditions and later measurement conditions help constrain the description of what occurs between them. Yet retrocausality in such models is carefully distinguished from retrosignaling, the ability to choose a message now and deliberately send it to your own past. Ken Wharton, for example, has developed retrocausal models in which future boundary constraints can help determine earlier hidden physical variables while still preventing controllable signaling backward through time. This distinction is crucial. An underlying theory might describe an event using information from both temporal directions without allowing you to receive tomorrow's lottery numbers today. And even among researchers studying time-symmetric quantum theories, there is no consensus that backward causation is required at all. Whether time symmetry truly demands retrocausality remains debated. The famous delayed choice experiments are a perfect place to see how easily language can mislead you. A photon can enter an experimental apparatus before the final measurement arrangement is selected, and later choices affect which correlations become visible when the data are compared. This can sound as though the future decision reached backward and changed what the photon really did. But the experiments do not provide a usable signal into the past, and analyses of delayed choice and quantum eraser setups show that their results do not require imagining the already recorded past being physically rewritten. The later measurement changes how the joint quantum data are sorted and what correlations can be revealed. It does not let an experimenter alter an earlier detector record after seeing it. That gives you three very different ideas that are often mixed together. Two observers disagreeing about which distant event happened first, a theoretical model allowing future boundary conditions to help describe earlier physics, and an actual controllable effect traveling backward to produce its own cause. Only the last would give you the dramatic reversal imagined in ordinary time travel stories, and no experiment has demonstrated it. Yet physics leaves the conceptual door open just enough to make the question profound. Many fundamental equations are far less committed to an everyday arrow of time than our memories are. We remember breakfast, not tomorrow's dinner. We carry records of earlier events, not later ones. Our lives therefore make causality feel inseparable from a one-way temporal flow. But at the microscopic theoretical level, physicists can construct descriptions in which the boundary between the past determines the future, and the full history determines the event becomes much less obvious. The effect may never literally appear before its cause in the laboratory, but asking whether it could forces you to confront a deeper possibility. Perhaps the forward direction of explanation that feels so natural to you is not identical to the deepest mathematical structure of nature. Would entropy run backward for someone traveling into the past? A traveler could arrive in yesterday while the broken glass in their hand keeps breaking rather than rebuilding itself. Because moving toward an earlier date is not the same thing as reversing the thermodynamic arrow inside your body. Entropy is often called the arrow of time because macroscopic systems overwhelmingly evolve from special, organized states toward more probable dispersed ones. Hot coffee cools, perfume spreads through a room, fuel burns, bodies age, and memories leave physical changes in the brain. Yet this thermodynamic direction is different from the direction a path takes through the coordinates of space-time. If a hypothetical closed timelike curve carried you into your own past, your personal clock could continue forward all along the journey. Your heart would beat in its usual sequence. Oxygen would continue reacting inside your cells. Heat would flow through your body, and the chemical processes sustaining consciousness would keep proceeding in the direction you experience as later. Nothing in the basic idea of a closed time-like curve requires every molecule in the traveler to reverse its velocity At the moment, the external calendar begins moving toward an earlier date. This distinction matters because popular images of time travel often combine two radically different processes: traveling to an earlier event and physically reversing an entire thermodynamic history. The second would be far more demanding. To make spilled milk leap perfectly back into a glass, you would need an unimaginably precise reversal of the microscopic motions and correlations of the milk. Table, air, emitted heat, and everything that interacted with them. The ordinary second law is statistical rather than a microscopic command forbidding every entropy decrease. But enormous spontaneous decreases in macroscopic entropy are fantastically improbable because there are overwhelmingly more disordered microscopic arrangements than carefully coordinated ones. The connection between entropy production and the distinguishability of forward and time-reversed processes makes this asymmetry mathematically precise. The more entropy a process produces, the easier it becomes to distinguish the real evolution from its exact reverse. A time traveler, therefore, would not ordinarily expect to see their wounds heal backward, meals reassemble inside their stomach, or memories disappear merely because their route through space-time ends at an earlier date. Their thermodynamic arrow could remain aligned with their own accumulated proper time, even while the external labels on clocks and calendars become earlier. Yet closed timelike curves make thermodynamics more subtle than this simple picture suggests. Researchers studying quantum models of such curves have constructed examples in which the effective dynamics can decrease entropy, showing that once you introduce exotic causal structures, ordinary formulations of the second law may require modification or additional assumptions. This is not evidence that a human time traveler would suddenly become younger. Those calculations concern hypothetical quantum models of closed time-like curves, which have never been observed in nature. They instead reveal that thermodynamics and causality are connected more deeply than a slogan like "entropy always increases" suggests. If a genuine time loop existed, the complete physical history might have to satisfy unusual global consistency conditions. And we do not yet possess a verified theory combining quantum mechanics, gravity, and thermodynamics strongly enough to tell us every consequence. The safest conclusion is therefore unexpectedly simple. Traveling into the past would not automatically mean experiencing thermodynamics backward. You could step into a year before your birth while remaining older with every second that passes for you. The calendar might retreat by decades while your cells continue accumulating damage in the only direction they know. And perhaps that would be the strangest proof that past and backward were never the same idea. You might stand beneath a younger sky, surrounded by events history calls earlier, while inside your own body entropy quietly reminds you that wherever space-time has carried you, your life is still moving forward. Could your memories move forward, while the world around you moves backward? If you watched a shattered glass rise from the floor, every fragment reconnect perfectly, and the water leap from the carpet into the restored glass while you calmly remembered seeing it break, then you would not merely be witnessing time run backward, you would be physically violating the symmetry required for a true reversal. Human memory is not an invisible observer sitting outside nature. Every memory you form requires physical changes in your nervous system. Neurons alter activity, molecular processes modify synapses, electrical and chemical signals propagate, and energy is dissipated into the surrounding body and environment. A new memory is therefore another physical record produced as your own thermodynamic history advances. Research on the relationship between memory and the arrow of time argues that the kind of memory humans use is closely associated with the second law. Present physical memory states contain detailed records of the past rather than equivalent records of the future, because their formation occurs within the thermodynamic asymmetry of our universe. Now imagine truly reversing the microscopic evolution of an entire room, not merely playing a recording backward, but reversing the states of every molecule, photon, sound wave, and neural process. If you were part of that exact reversal, the physical changes that formed your memories would reverse as well. Instead of accumulating a new memory of the glass reassembling, the neural record associated with watching it break would progressively undo itself. From inside such a perfectly reversed physical process, there may be no observer carrying an untouched forward-moving diary through the reversal, because the diary, the brain, and the observer are themselves pieces of the system being reversed. This exposes the hidden contradiction in the familiar fantasy of walking normally through a world that is literally running backward. For you to retain old memories and form new ones while everything else reverses, your body would need to remain thermodynamically forward while the environment followed an opposite arrow. You would effectively be a foreign subsystem with different boundary conditions. The moment you interacted with that environment, however, you would disturb the perfect reversal. Your eyes would have to absorb photons that, in an exact time-reversed history, may instead need to leave your eyes along precisely coordinated trajectories. Your lungs would exchange molecules with reversed air. Your feet would transfer heat and momentum to the floor. Speaking would generate new sound waves rather than perfectly absorb the sound waves corresponding to reverse speech. Even observing the backward world would couple you to it, producing new correlations that were absent from the exact reversed history. In other words, keeping your memories moving forward would make the world's perfect backward evolution increasingly impossible. This is related to the deeper statistical nature of irreversibility. At microscopic scales, many fundamental dynamical laws can describe both forward and reversed motions. Yet ordinary macroscopic reversal requires extraordinarily precise correlations. Slight disturbances destroy that coordination and restore the familiar entropy-increasing direction. Quantum studies likewise show that unusual pre-existing correlations can produce local reversals of the thermodynamic arrow, but such behavior depends on specially prepared states rather than representing a world casually running backward around an unaffected observer. So, if a hypothetical time machine merely transported you into the past, your memories could continue accumulating normally because the surrounding world at the destination would also continue evolving forward from that earlier date. You would remember the future because you personally experienced it before arriving, not because everyone else was physically reversing. But a universe literally rewinding around you creates a different problem. Either your brain rewinds with it, threatening the very memories that would let you notice the reversal, or your brain remains forward-moving and begins contaminating the precise conditions needed for everything else to reverse. That is why the image of standing still while rain rises into clouds and people speak backward is far less physically innocent than it appears. To remember a reversed universe, you would need to remain outside the reversal just enough to observe it. But observation requires interaction, and interaction would make you part of the thermodynamic story again. The deeper paradox is therefore not whether memory could survive backward time. It is whether anyone embedded in a perfectly reversed physical world could possess the forward-moving records required to recognize that the world was reversed at all. If time had a beginning, could you travel to before the universe existed? The most impossible destination on a time machine may not be the distant past, but a moment for which the word before has no meaning at all. When you imagine traveling toward the beginning of the universe, it is natural to picture the cosmic clock counting backward. Galaxies disappear, stars dissolve, atoms break apart, everything becomes hotter and denser, and eventually the clock reaches zero, leaving some dark emptiness on the other side, waiting for you to enter. Modern cosmology gives us no reason to expect that final image. The Big Bang was not an explosion occurring at one location inside pre-existing empty space. It describes the early expansion of space itself from an extraordinarily hot and dense state. NASA's John Mather emphasizes that the Big Bang happened everywhere rather than at a central point. And observations allow us to reconstruct the universe back toward its extremely early stages. Though not to simply watch a literal first instant, whether time itself truly began at a finite boundary is a deeper question that present physics has not settled. If it did, then asking to travel before that beginning could be like asking to walk 1 kilometer north of the North Pole. Not because a guard blocks the route, but because the direction you are requesting has ended. A time traveler needs a world line, a continuous sequence of events through space-time. If there is no earlier space-time region, there is nowhere for that world line to extend. Your machine could become arbitrarily powerful and still face a problem no engine can solve. There would be no earlier date to enter, no empty room outside the universe, and perhaps not even a meaningful clock on which the requested destination could be written. But cosmology is not yet certain that this is what happened. Theories of cosmic inflation describe an extremely early period of accelerated expansion, and an important theorem by Borda, Guth, and Vilenkin shows that a broad class of sufficiently expanding spacetimes cannot be extended indefinitely into the past along certain trajectories. Crucially, the theorem does not tell us what lies at that past boundary, or prove that absolute nothingness preceded it. It tells us that inflation alone is not a complete description of the infinitely distant past. Other proposals replace the classical beginning with something less intuitive. Quantum cosmological models have explored a universe with no ordinary past boundary, while bounce models and other speculative ideas allow an earlier phase from which our expanding universe could emerge. None has been experimentally established as the definitive description of cosmic origins. Even NASA's current overview of the early universe notes that scientists do not know what preceded inflation or what powered it. This distinction completely changes the time travel question. If an earlier cosmic phase actually existed, then before the Big Bang might eventually become a legitimate physical phrase, though reaching it would involve physics far beyond any known technology. If time genuinely began, however, no amount of backward travel could carry you beyond it, because traveling backwards still requires time in which the journey can occur. You could perhaps approach the earliest meaningful moment the laws permit, watching familiar concepts of matter, temperature, and eventually, even classical space-time lose their ordinary definitions. But there would be no final door marked before the universe. And perhaps that is the deepest limit a time traveler could encounter. Not a wall at the beginning of history, but the discovery that the map itself has stopped. You could ask what happened 1 second earlier, then a smaller fraction earlier, and continue pushing language toward the boundary until eventually, physics might answer not with another event, but with the unsettling possibility that there was never an earlier moment waiting to be visited. If time travel were possible, how would we ever know it had already happened? A real time traveler could have walked through history without leaving anything that looks like a time machine, which means proving that time travel had already happened might be harder than discovering the traveler themselves. Imagine finding a photograph from 1920 containing someone wearing suspiciously modern clothing. That would be intriguing, but it would not be proof. Clothing can have unexpected historical precedents. Photographs can be altered, dates can be mistaken, objects can contaminate archaeological sites, and extraordinary coincidences occur. Even discovering a modern-looking device buried in an ancient layer would first trigger far more ordinary explanations. Fraud, later intrusion, incorrect dating, contamination, or misunderstanding of the artifact. Science does not identify time travel by deciding that something looks impossible. It would need evidence whose origin could be tested and whose ordinary alternatives could be progressively eliminated. A much stronger clue would be information that could not reasonably have been available when it was recorded. Suppose a document securely sealed in 1950 contained the exact locations and detailed properties of astronomical objects that would not be discovered until decades later, or a long sequence of genuinely unpredictable future measurements recorded with enough precision that lucky guessing became overwhelmingly implausible. Even then, you would need to establish independently that the document truly existed in 1950 and had not been modified afterward. The strongest case would probably require repeated, controlled demonstrations rather than one spectacular artifact. Information arriving before it became conventionally obtainable, with timestamps and custody verified by independent observers, and predictions chosen so that knowing them could not easily cause them to happen. This last requirement matters because once future knowledge changes human behavior, the evidence becomes entangled with the event it predicts. Astronomical observations, radioactive outcomes recorded under carefully designed conditions, or other events difficult for the recipient to manipulate, could provide cleaner tests than lottery numbers or political predictions. Scientists have actually tried a modest version of this search. Robert Nemiroff and Teresa Wilson searched the internet for apparently prescient references to information that was not yet publicly known, examined search activity for future terms, and even issued a request asking future time travelers to send a message that would predate the request. They found no evidence of time travelers. The authors were careful to note that this negative result does not disprove time travel. It only means their search found none, and that reveals the deeper difficulty. A traveler would not necessarily want to announce themselves. They might arrive in a period without digital records, interact only briefly, or leave traces indistinguishable from ordinary history. If time travel operated within one self-consistent history, every intervention might already be woven into the records we possess. The mysterious anonymous donor who funded an invention, the stranger who gave someone crucial advice, or the unexplained object described in an old letter would not suddenly glow with a label saying, "From the future." It would simply be another unexplained event in the past. Even advanced knowledge would not be decisive unless its provenance could be established, because humans independently discover ideas, fabricate stories, and occasionally make astonishing predictions by chance. There is also no accepted physical signature that every hypothetical time traveler must carry. Relativity does not say a visitor from 2400 would emit a special radiation detectable by modern instruments, and no established experiment can scan a person and read the century from which their world line originated. Their atoms would still be atoms. Their blood would still obey chemistry. The evidence would have to come from history, information, or the machinery that transported them. This means a civilization could conceivably overlook a genuine traveler if the evidence were weak enough, while simultaneously misidentifying countless ordinary anomalies as time travel. The standard of proof has to remain high precisely because the claim is so extraordinary. So perhaps the final paradox of time travel is epistemic rather than temporal. If no traveler has ever arrived, the world should look much as it does now. But if travelers arrived carefully, left no uniquely testable technology, and became part of the history we already know, the world might also look much as it does now. We search for impossible fingerprints, yet a perfectly integrated visit might leave none. And after 60 questions about changing history, looping through time, bending space-time, and meeting the future, you arrive at one final uncertainty. If someone from tomorrow had already stood somewhere in yesterday, the hardest problem might not have been traveling through time at all. It might have been giving the rest of us enough evidence to know they were ever here. Could you give Shakespeare his own plays before he wrote them? Imagine arriving in London around 1590 carrying a printed copy of Hamlet, placing it in William Shakespeare's hands, and watching him read words that history says he will not write until years later. At first, this sounds like a simple joke about time travel, but it creates one of the strangest questions about authorship imaginable. If Shakespeare copies the play from the book you brought, performs it, and eventually produces the version that survives into your century, then who actually wrote Hamlet? You obtain the text because Shakespeare was historically credited with writing it, yet Shakespeare obtained the text because you delivered it from the future. The words move through a closed chain without an obvious creative moment. But unlike an abstract mathematical formula, a play is more than information arranged correctly. Shakespeare's works emerged from a particular linguistic world. Elizabethan theatre, contemporary politics, older stories, religious assumptions, acting companies, printing practices, and the rapidly changing English language. Many of his plots were adapted from earlier chronicles, poems, legends, and plays rather than invented from nothing. Giving him a finished future edition would therefore inject not only his supposed future work into the past, but centuries of editing, spelling modernization, scholarly reconstruction, and publishing choices that accumulated after his lifetime. The text you hand him might contain punctuation conventions he never used, line divisions chosen by later editors, or readings reconstructed from quartos and the first folio. He could be receiving a version of his work, partly shaped by people born long after him. And then history becomes wonderfully tangled. Perhaps he changes unfamiliar wording, perhaps actors alter lines during rehearsal, perhaps printers introduce new errors. The play that eventually reaches your future could therefore differ from the copy you originally carried, raising the question of whether a perfectly closed literary loop could even remain stable. Real texts mutate as humans copy, edit, perform, and reinterpret them. There is also a deeper issue. Authorship is not merely possession of words. If Shakespeare never struggled through the decisions that produced the play, can he still be called its author simply because he published it first? You might have removed the act of creation while leaving the reputation intact. No experiments suggest that such a loop can occur, because backward time travel has never been demonstrated. But the thought experiment teaches something real about information. Knowing where a work appears in history is not the same as knowing where its creativity originated. If you handed Shakespeare his own future masterpiece, the greatest mystery might not be how the book crossed centuries. It would be how a work could become famous, performed, studied, and loved for hundreds of years, while its first genuine moment of invention was nowhere to be found. Could you bring a future invention into the past before anyone invents it? Dropping a modern smartphone onto a laboratory table in the year 1900 would not instantly give the world smartphones a century early, because an invention is rarely just the object you can hold in your hand. Inside that small device are technologies dependent on an enormous hidden civilization of knowledge: semiconductor fabrication, ultra-pure materials, microscopic transistors, advanced optics, lithium-ion chemistry, precision manufacturing, satellite navigation, digital communication standards, software, and factories capable of controlling matter at scales early engineers could not approach. A scientist from the past could open the phone, examine its layers, perhaps recognize metals, glass, coils, magnets, and batteries, yet many of its most important components would reveal almost nothing to the naked eye. A modern processor can contain structures so small that understanding its design requires instruments and fabrication methods that themselves took generations to develop. This illustrates the difference between an artifact and the technological ecosystem that makes the artifact reproducible. Archaeologists can understand the shape of an ancient tool because its method of manufacture may be visible in the object. Advanced electronics hide much of their manufacturing history inside materials, whose useful properties depend on controlled impurities, microscopic geometry, and processes the finished product does not explain. Even if you brought detailed manuals, another barrier would appear: tacit knowledge. Engineers know many things that are difficult to capture completely in instructions. How to diagnose contamination, tune machinery, interpret failures, control production tolerances, and recognize when a process is drifting. Technology grows through networks of skills, suppliers, measurement standards, failed prototypes, and previous inventions. So a future machine placed in the past might accelerate certain discoveries without allowing anyone to reproduce the machine itself. A 19th century physicist examining a laser pointer, for example, could learn that an extraordinarily concentrated beam of light is possible, but knowing that the effect exists is very different from possessing the semiconductor materials and manufacturing chain needed to build another one. The object could still transform history simply by proving that certain goals are achievable. Engineers often waste years asking whether something can be done at all. A working artifact answers that question immediately and could redirect research toward the right principles. Yet there is a quiet danger in assuming that progress would simply leap forward. Some inventions depend on earlier infrastructure so deeply that revealing them prematurely might produce decades of frustration rather than instant advancement. You could bring back the destination without bringing the road that leads to it. And that changes the meaning of invention itself. We like to imagine technological breakthroughs as moments when one brilliant person has one brilliant idea. But most modern inventions are layered structures built from thousands of previous discoveries. If you carried one of them into the past, you might discover that the remarkable thing was never merely the device. It was the vast, invisible chain of human knowledge required to make that device possible at all.